So we will start our first talk soon. And before the first talk, I want to make some announcements. Again, I announced yesterday, but let me say it again. That today's last talk would be given by Professor Chung to give more introduction about the normalization group. So I may use like 10 or 15 minutes to quickly show you some example of tensor network, but just very quickly, and the rest of time will be given by Professor Chung. So, let's see the pronunciation. Two more minutes. Sorry. Okay, so let's we can start our first talk today. So today we'll have more numerical method talk. And today's first talk was given by Professor Ian McCulloch, and he has been in Queensland University in Australia for a long time, and recently we are lucky that he moved to NSYSU University, so just very close. So yeah, it's very convenient to discuss with him. And he's an expert of this metric product state, this network state. And as I said yesterday, all of this tensor network algorithm start from the DMRG algorithm, which originally is not even in a metric product state format. And I think Ian is the first guy to realize that okay, DMRG can actually be be written in a metric product state form. And with that, now most of people understand DMRG using metric product state. And with this structure, you can really do many more things, on top of not just DMRG. Now you can do on top of MPS, you can do a lot of things. Then he will give some of the application using yes. It's many about the time. So let's go.
Yeah, thank you. Yeah, it's nice to be here. Nearly a full room again. Yeah, so today I'm going to talk about, it's kind of like in two parts, I guess. I'm going to cover fairly quickly both parts, actually, because there's quite a lot here, and just review some applications of time evolution, of what sorts of calculations can I solve using MPS time evolution algorithms. Just kind of a snapshot, really, because there's a huge amount of work that people are doing. We can't expect to cover it all just in an hour. So we're going to look at some example calculations that we've done in the past using MyCode's what's called the matrix product toolkit, Something I'm not going to include is dynamical quantum phase transitions. Algorithmically, there's nothing really new here. It's essentially a quantum quench, which I will talk a little bit about. So in the second half of the talk, I'm going to talk about a little bit of the physics of time evolution, like why is it actually hard, and then I'll review very, very quickly, no real technical details, the different algorithms, and just to give an overview as to how they work. So the idea being that if you come to, I want to solve this particular problem, what would be the best algorithm to use here? Or if you grab a code, say if you use iTensor or the toolkit or some existing code, what algorithms is it likely to have, and which ones should you be aiming at? So we're certainly not going to actually present any code or how to actually write one of these codes. There's sort of plenty of documentation online, I think, if you want to do that. Okay, so first up, why do we want to calculate time evolution? I think one of the principal things you want to do is to calculate the spectral function. So we can do that numerically. It's also got a real like physical importance. It tells you very interesting physics about your system. So the spectral function is the imaginary part of our Green's function in energy space. So essentially, we're doing a Fourier transform with the retardant part of our Green's function. So if we see a peak in our spectral function, for example, that will correspond to some kind of quasi-particle in our system. It means that when I'm applying my operator A to my state, that's exciting some specific particle in my system. So the width of it gives the lifetime or the scattering rate. If it's a very narrow, sharp peak, then I've got a very well-defined particle. If it's a very wide peak, then it's something very incoherent. It's some kind of scattering into many different particle states. So the momentum dependence of my spectral function gives me the velocity, the dispersion relation of my particles. There's more details in there, so we get Hubbard bands, Kondo resonances, for example. We can see it's related to the optical conductivity and the magnetic susceptibility, transport properties. So if I've got linear response, I've got the Kubo formulas that relate our spectral function to the conductivity. And there's direct experimental measures that will essentially give you this function pretty much directly, including ARPES, inelastic X-ray scattering, and so on. And many of those techniques are actually done like in Taiwan as well, like just over here. Well, I'm not sure which direction. Okay, so a very simple example. So this is some work of a former student of mine. So this is, well, it's actually physically it's a very, very simple example. It was a technical paper on the methodology. So this is a Heisenberg spin chain for now S equals 1. So not half integer spin, but spin 1. So this is this sort of famous Haldane chain. It's a gapped spin liquid. So what we see here as a function of the momentum Q here and energy direction, we see we get a very sharp peak at k equals pi, and it kind of disappears as we go to momentum 0. If we look at this in the flat direction, we see a very nice spectral function here. If you look at the peak, if you look at where the maximum of the peak is in energy, then we get a dispersion relation here. So what we can immediately see from this is that the excitations are gapped. So there's this minimum energy we need to excite an excitation, and this is the Haldane gap here, which is, I think, even gets that to a few digits, which is quite good for a very simple calculation. So we have a very strong peak here. So we have well-defined quasi-particles at momentum pi. So we get a Magnon excitation here. This Magnon excitation, as we go to smaller momentum, we go near momentum 0, the weight of that quasi-particle disappears. So physically what's happening here is that it's disappearing into a continuum of two particle excitations. So what can happen is if my momentum is small, what can happen is that instead of generating a well-defined Magnon, I'm generating a 2 or higher particle state of momentum near pi, right? That if I've got two particles at momentum pi, my total momentum is 0, right? And I can do that with an energy that's twice this. So I can do that with an energy of like 0.8, essentially. So up here somewhere. So I'm going to get that rather than a state of some high energy that corresponds to my single Magnon.
This is obtained by first compute the correlation function and do the Fourier transform.
Right, exactly. Yes. So this is what we want to calculate. The most common way is to calculate a real space dynamical correlation function. So that is, I act with my operator on a specific site of my lattice. So we get that. It essentially means we can do this in one shot, get all of the momentum. It is possible to do this directly in momentum space. I act on my operator at some specific k value, and then I do the time evolution and Fourier transform that. In principle, actually, that's quite accurate, but it means that I have to do every k point separately. Right? If we imagine, well, if I just do like a delta function in real space, then this is in principle, an equal weighted superposition of all possible momenta. Right. So if I do it in real space, I just apply a local operator. Like, so in this case, it's the S plus operator. I apply the S plus operator at one point of my lattice, and then I do the time evolution, and I look at the correlation function of that. Then I can Fourier transform it both in real space and momentum space. Sorry, into frequency space and momentum space. I do a double Fourier transform. So we express that as an expectation value of this quantity here. So what I'm doing here is I write down, I can express the time dependence of my operator, sort of like Heisenberg picture, I guess. Now, this term here, because my psi naught is an eigenstate, right? I don't actually need this one here, right? This one just comes out and it's the ground state energy. So the only time dependence I've got is this one in the middle. So what I need to do then is I need to act on my ground state with my A naught, or S plus in this case. I calculate the time evolution of that state, and then I calculate the expectation value with the annihilator acting at some other site of my lattice. So the key step, or what's the numerically expensive part, is to calculate the time evolution of this local perturbation here, of this quantity here. And actually in this paper, the new part of what we were showing in this paper was that we can do that some kind of like locally. I don't have a picture of that, but what we started from was a translationally invariant infinite MBS of my ground state. Then I break that translational invariance by applying my S plus operator at one site. Arbitrary, it doesn't matter because it's all translation invariant, and then do the time evolution in like kind of a window that's slowly growing as my wavefronts are spreading out from that site. So up until this point, everyone had done this just on just choose a finite size system that's big enough to contain the final time evolved state. The problem with that, of course, is that if you decide right at the end, oh, my system's not quite big enough, I want to do more time evolution to get more resolution, then throw away that calculation and start again with a larger lattice size, which is a bit of a pain. Okay. Yeah. Okay. So the next kind of sort of sample application we're going to look at is what's known as a quantum quench. So the idea is that we prepare our system in some initial state, which is typically a ground state or some thermal state of some Hamiltonian H naught, and then at time t equals 0, I'm going to suddenly change something. So this is something you could do in an experiment. Well, as a theorist, I could say, as an experiment, you just go to your device and you suddenly turn it on in some direction, and suddenly change your Hamiltonian. So in practice, it might be that you change the strength of your laser and you change the depth of your optical lattice or something like this. So then the system evolves under the new Hamiltonian. So it could be a local quench that we change the Hamiltonian in some finite region. Maybe we just turn off the edges of the trap or something like that. Or it could be global, like maybe change the interaction strength, and we see what happens. So certainly an interesting case would be if you change the interaction strength such that the ground states of your new Hamiltonian would actually be in a different phase to where you started from. So in optical lattices in particular, this is where many of these kinds of experiments are done. You could quench the interaction, for example, across a Fesch-Park resonance. You can tune the interaction very precisely. We can tune the lattice depth as well, which will control our tunneling rates. Or we could quench an external field. So we could put an electric field or a magnetic field in our system. So as an example of that, there's some old work. So experimental collaboration with Ulrich Schneider's group of an expansion of a Mott insulator in one direction. So the scenario here is that we imagine that we've got some bosons in an optical lattice, and at t equals 0, we're going to release the trap. So then they're free to expand in one dimension. And we looked at this for a single chain, essentially, and we also looked at this at a two-leg ladder. So the idea is there a difference in dimension, like as you go from 1D to 2D? Argue, okay, a two-leg ladder is not very 2D, but well, it's more 2D than just a single chain. And actually, as it turns out, that the two-leg ladder already captures essentially the essential physics that you'd expect to get in 2 dimensions. So what happens here then? We prepare this larger system with the trap, so the particles are confined to the middle of my system, and then at t equals 0, we just remove that confining potential and allow the particles to expand at the edges of the system. So if we do that numerically, then we see a big difference between the superfluid phase and the Mott insulator here. The superfluid basically just stays there, sort of a little bit of expansion just at the edges. But for the Mott phase, then we see essentially universal. It doesn't really depend on the interaction strength in any essential way. And in particular, the velocity of propagation here is independent of U. I think it's like root 2J or something like this, I think. And this actually can be realized experimentally. So in this plot here, the bottom half is numerics. It's basically the same. It's a different paper. It's a different calculation to this one, but it's essentially the same setup. The top one here is actually experimental. So that's actually X-ray scattering, I think, of an optical lattice of potassium ions, I believe, in an optical lattice. And you can see, yeah, there's certainly some differences between the numerics and the experiment, but it kind of captures the main idea, I think. So if we compare that for the 1D system with a two-leg ladder, what happens in the two-leg ladder is now that we do get big differences. So rather than having this essentially ballistic transport where our particles just move out at fixed velocity, what we have is that core essentially stays stationary. So this again is the numerics experiment. These are not quite the same setup. So here we've got a two-leg ladder where we're changing the interaction strength, changing U. In here, what's happening is it's changing the transverse coupling. So chi is this ratio of the jy to the jx of hopping in the transverse direction. So this is essentially the 1D case. This is essentially the 2D case here. And that agrees actually pretty well. As you get to the 2D case, that's pretty comparable to this case here. Okay. So it's actually some quite nice results, I think, in the end, where our numerics are very directly comparable in a quantitative sense, even with some real experiment, which is very nice. Okay, so yeah, not quite a different topic, but I'll say an alternative to calculating time evolution, an alternative kind of approach is to calculate the low-lying excitations of my system directly. So in fact, this is a very old idea. It dates back to 1995. So this is one of those kind of key papers that actually first pointed out the connection between density matrix renormalization group, which was only a few years earlier, 1992, 1993, and matrix product states, which already existed in, I guess, the mathematical physics literature at that time. And this paper is actually still very interesting to read today because the appendices actually covers how to construct excitations above the ground state, which is a technique that really wasn't revisited properly until, I've forgotten the dates now, 2011, 2012, maybe. So it was really well ahead of its time, that paper was, but of course this paper here, yeah, 2012. Yeah, so it was really like well ahead of its time, this paper here. So the idea is that if we start with a ground state, so we can imagine that this is translational invariant, infinite. So I just take my tensor here that Charlie introduced us to yesterday, and I just pretend I've got infinite copies. Of course, on my computer, I only have one copy of this, but we pretend it's infinite. Then the excitation ansatz I can think of as a sum of all possible translations of doing a local change of this. So I replace one of my tensors here with a B, and then I sum up all possible translations of that with a momentum factor out the front of K. So I multiply it by e to the ik every time I do a translation. So, for example, if my excitations are, in fact, quasi-particles, if my excitation is, for example, just a non-interacting, say if it's an S plus operator exactly, then I know what that B is. I don't even need to do a calculation here. I can just say that this B is equal to the local S plus operator acting on my A matrix, acting on the physical index of my A's. But if we don't have that, if it's an interacting system, or if it's any kind of interacting system, then I need to variationally optimize my B tensors here. And there's a kind of a DMRG-like algorithm to do that. So we just minimize the energy of the excitation subject to varying this B tensor here. So if we do that, then we can get the set of low-lying excitations as a function of the momentum K. So that's an input into this algorithm. So as an example of that, this is a numerical calculation. Again, sort of a bit of a benchmark calculation from a paper that actually we might even submit this week from my student, Jesse Osborne. And this is, again, the spin 1 Heisenberg model that we saw before. So this line here is the same single magnon line that we saw earlier, but now it's calculated directly by finding the eigenstate, the excitation state of my Hamiltonian. So the difference now is that at every point here, at every K point, I'm not sure how many, maybe 100 or more, we explicitly have the wave function for my excited state at that point. So that's very versatile. It means I can calculate expectation values and all sorts of things once I've got my wave function. So, for example, we can calculate the quasi-particle weight. Right. So I can ask the question. Well, now I've got my single magnon state. when I go back and look at my spectral function, what is the weight of that quasi-particle? Or in other words, what is the overlap between my Magnon state at my K with my S plus operator at the same momentum? So I don't need to do a time evolution calculation for that. I just calculate this expectation here, this expectation value directly. So I've got the operator, I know what the operator is, I've got the two wave functions, I've got the ground state, I've got my excitation at momentum K. So that's a very nice demonstration of what we can do. We can also calculate, for example, the particle velocity. So if you want to take some point here and say, well, what's the slope? Well, one way to do it would be to do some kind of finite difference, right? Just numerically calculate the slope here. Another way is we can just calculate the derivative directly with respect to K of this expectation value. And that has a very nice form as one of these like sort of triangular MPO, MPS kind of thing. So there's a better way of calculating the velocity here rather than just numerically doing a derivative at different values of K. Okay. And something else we can do with this approach is now that we've got this whole bunch of psi of K objects, we've got if we've got, for example, all possible momenta, then we can construct wave packets. So for a wave packet, we can construct that as an integral over all possible momenta of any function we want of the momentum. So for example, we could choose it to be a Gaussian centered at some momentum Q with whatever width that we want. It could be a very narrow, or it could be fairly broad. I think you don't want it too narrow because what's going to happen is that then in real space it's going to be very, very wide. So you want some kind of minimum uncertainty sort of wave packet. So you can make some Gaussian with some width. And what we did, or in fact what Jesse did, was for the fermionic Hubbard model now, we can do that for a spin excitation, and we can do that for a charge excitation. So we've got two wave packets now. One is like an S plus kind of operator for a spin. Another one is like a C dagger operator for a charge. And you can split these up. So we've got the excess charge in one part of our lattice and the excess spin at the other. We choose the momentum of these such that all of the momentum of the excess charge is pointing to the right, and the momentum of the spin excitation is pointing to the left. So hopefully the movie works. So then we've got our rule space wave packets. We can point them at each other and then collide them. So we can see what happens as they pass through. Right, we actually see nothing, which is actually exactly what we want. Right, that we've got spin charge separation here. So the spin degrees and the charge degrees of freedom are actually independent, propagate at separate velocities. We might think, well, that's just very trivial, but actually it's not here because we've got a very highly entangled many-body wave function, and that many-body wave function includes all of the spin and charge degrees of freedom all in together. So it's actually highly non-trivial that these particles, that these two wave packets will actually pass through each other. And it's certainly the case that they do have an influence on each other. That if you look closely, there's a background spin, there's a slight background spin antiferromagnet. Okay, up, down, up, down, up, down. If you look carefully, what you see is that there's a domain wall in that background spin fluctuation as the charge wavefront moves past. I think you can't really see it on this picture because there's some averaging to smooth out these fluctuations, but there's a domain wall in a spin structure corresponding to the location of the charge peak.
Yeah. So into the previous slide. So this phi k is exactly true.
Yes. Yep. Yep. Yeah. So we do this twice. We do that once where phi of k is my charge excitations, and again separate calculation where my phi k is my spin excitations. So then we get that in as two real space wave functions, and then we'll just join them them together. Of course, there's lots of technical details in there as to how do we join these together, you know, with a smooth boundary between them and so on. So there's a lot of details hidden, but it's all, in the end, it's actually all very quite well controlled and a quite well defined process. Yeah, actually, I should say, please interrupt with questions at any time as we go through.
So
yeah.
In practice, you make psi as NTS. You explicitly construct this as
yes, yes.
With huge problem.
No, actually, I think about 100 or so for this calculation. Yeah. I mean, if you want to get it very accurate, then you need increased one dimension. But yeah, no, this is quite relatively small. Yeah.
So, so this is a one-dimensional Hubbard model,
right?
Of fermions. So, is there other approaches, analytical and numerical, that could study this time evolution of the spin and charge excitations, like bosonization?
Yep.
Or conformal field theory?
Yep.
Or this is so far the only way?
Yeah, okay, so spin charge separation has certainly been known for a long time.
That's right.
Right, from that ansatz solution, the conformal field theory. But what hasn't been done, as far as I know, I don't know of any other method that actually lets you calculate something that's comparable to this.
Yeah, this is very new.
Yeah. This I think is very new. So I think when time-dependent DMRG first came out and people were doing these kinds of calculations, I mean, I did a very early one in back sort of 2005, 2006 kind of time, where you just start from a finite system and you just excite apply a C dagger with some spin at the boundary, and what you do then is you see that the spin and the charge excitations are propagating with different velocities.
This is not the time-dependent DMRG.
This part is here. Yes. So what we're doing is we construct our wave packet. So this is the initial state at time t equals 0, and then we do the time evolution of that, and we see the two wave packets propagating. Yeah. So the physics of this has all been mostly well understood for a while, right? That this decomposes. You can write it as a kind of some semi-direct product of two conformal field theories that have the different velocities for the spin and the charge, and so on. So this has all been, quite well understood as to mathematically how this works. But certainly from the beta ansatz, even calculating correlation functions from the beta ansatz is really hard work. Never mind actually calculating all of these excited states and looking directly at these kinds of wave packet evolution. So yeah, I don't know of any other method that can do anything comparable to this calculation. Yeah. Okay. Yeah, so I'll talk a little bit about thermal states as well. So far, everything we've looked at has been ground state plus very low energy excitations above that. So if we want to calculate a thermal state, what we need is, instead of a wave function, we need to do our simulation using a density operator. Right. So I can think of that. Well, I've got a basis for my wave function I. Now I need to promote that to being a density operator. So I essentially need to double the size of my basis. So as well as a ket state I need a bra state J. So you can actually think of that now, that instead of having just like a 1D wave function, I've now got a two-leg ladder, but where I've doubled the number of physical degrees of freedom. So one way of thinking about that is like a purification. I've got my two-leg ladder, and one of those legs of my ladder, I'm just going to pretend that instead of a ket, it's actually a bra state. So now my physical state is actually an operator rather than a state. So in fact, you can formalize that if you want to, one way of doing that is just to regard this two-leg ladder directly as my density matrix. Another way is to regard this as a purification. So I treat my physical density matrix as a contraction of my two-leg ladder multiplied by its conjugate, meaning here that I'm going to contract over my so-called ancilla index J here. So I've got a physical one leg for the physical part of my system, say the I leg, and the J leg will be the ancilla, and then to construct my physical density matrix, I'm going to multiply it by its conjugate and contract over that J leg. One advantage of this construction, for example, is that if I've got something that looks like A times A dagger, I'm guaranteed that this is positive. Whereas if I just write down some generic operator here, well, my density matrix, it should be positive, but there's no way numerically to actually guarantee that it will be positive in this context. In principle as well, you could try and disentangle this ancilla. That's a bit of a technical topic. But in practice, I don't know of any good algorithms to do that. Yeah, so we can think of so for example, if I try and write down, well, what is the density operator corresponding to my ground state? But if I use the density matrix directly, then my ground state just looks like the bra and the ket, both being the ground state. So we can think of that to essentially just two copies of my ground state, one of them in this leg here, and the other one in the top leg. And then if you look at what bond dimension does that correspond to when I make a cut, it's actually, I've gone from bond dimension D to bond dimension D squared, which is bad, right? So if I've got bond dimension, say 100, that's fine, that's gonna be fast. I square it, now I've got bond dimension like 10,000. That's actually crazy slow. So that's really a huge difference between say doing a ground state versus a density operator at low temperature. On the other hand, if I use the purification scheme, then I can represent my purification just with some product state in the other side, because my physical density matrix, I get that by doing A times A dagger and contracting over the middle one here, which gives me back my ground state density operator. But the bond dimension of this, because one of these is a product state, bond dimension 1, it's much more efficient. But again, I actually don't know of any method that will actually do that physically, that if you try to, say, construct from first principles this operator here, I don't know of anything that will disentangle it down to this product state. So technically, yes, this is a nice idea, but I don't know in practice how to actually do that. Okay, so how do we actually calculate this thermal state? Well, if we want to calculate some state at some temperature, 1 over beta, then what I need to calculate is the exponential of minus beta times h as an operator. Well, okay, if we choose infinite temperature, then this is very easy. If I choose infinite temperature, beta equals 0, then my density operator is just the identity. So I can calculate that very simply. It's got bond dimension 1 effectively. But now we can evolve it in imaginary time to the desired value of beta. So what I mean by that is if I can construct for a very small value of beta, like delta beta, I can do some kind of expansion of my evolution operator, and then I can multiply that together many, many times. Or, for example, you could repeatedly square your operator. That if I've got a very small delta beta, then I can square that. I can square that operator, and suddenly I've got 2 times delta beta. I can square it again, and I've got 4 times delta beta, and so on. There's an alternative approach, which is to sample over low entangled states, the so-called METS algorithm. So for more details, there's a reference. There's a reference there. So I didn't put up an example. Yeah, I didn't put up an example of a thermal calculation. I haven't done too much of this myself. I couldn't find a sort of a nice picture that really summarized what people are doing. It's certainly used a lot less than pure state calculations in DMRG, but yeah, it's certainly usable. You can do it. Okay, so are there any questions so far about the kinds of calculations? Yeah.
So if I consider direct state evolved by chosen processes,
Right.
can you adapt your method?
Yeah, we can. So I don't have a slide on that, but if you want to evolve it according to some Lindblad equation, then yes, you can do that. Just instead of doing this imaginary time evolution with respect to the Hamiltonian, putting in Lindblad operators here is no problem at all. Yeah.
Instead of the purification.
Right. Okay. For the purification with the Lindblad, yeah, that's a little more complicated, I think. Yeah. Actually, I don't know off the top of my head how to do that, but yeah.
You have to map it to like the distance operator.
Right.
Basically, with the Lindblad will which is what trough mapping. So it will become
Yeah. Okay.
So then your density matrix will become the prime here. And then you follow it.
Yeah. Right. Yeah.
But then basically
Yes, I mean in principle, but in practice, I think actually finding a good purification that is actually very hard. And it's probably something we could talk about later. But I think the normal approach to finding these purifications is to do some kind of disentangling, local disentangling. But actually, it turns out that that's completely the wrong way to do it because the extra, I'll talk about it shortly. But the extra entanglement you get is actually at long range, not short range. And I don't know of any good way of removing long range entanglement from the purification. Maybe, but that's also also complicated. But yeah. Okay. So time evolution. Why is it kind of hard to do in practice? So there's kind of a key problem here that the entanglement grows when you do time evolution. So it's pretty much a general theorem that if I have a global quench of my system, that I do time evolution from some initial state, that the entanglement of my system will grow linearly with time up until it reaches essentially a volume law entanglement, that the entanglement of my state is proportional to the size of my system. So if I'm simulating a big wave function, then the entanglement can get very, very huge very, very quickly. So what that means actually, if I want to represent a volume law entangled state, there's actually no advantage to using a tensor network for that. You might as well do exact diagonalization. The bond dimension you need is exponentially big. This is a problem because essentially all of that entanglement is kind of spurious. It's like the complicated many body correlations that you actually can't even, in principle, you can't even measure them. So physically, it would be possible to represent, say, the long time evolution, some kind of thermal state or sort of quasi-thermal state. But practically, it's very, very hard to do that because we get this entanglement growth of this spurious entanglement. So this is a figure that I took from this paper here from Calabresi and Cardi, which is an exact solution. It's a quench in the transverse field Ising model from H naught equals infinity. So say an eigenstate of sigma x, quench it to the critical point at H equals 1. So what we see here is that the entanglement grows until it saturates at the given lattice size. And what you see here, so this is the derivative. So what we see here, the entanglement growth in time is constant. It's perfectly linear until it saturates at some size given by the lattice size. So this is really the key problem that you have to manage numerically, that the simulation, in principle, the simulation is exponentially difficult with respect to the simulation time that you're evolving to. Okay. So that's the case for a global quench, that we get the linear growth. If we do a local quench, say if I just have my system and locally I perturb my Hamiltonian, or I start from an eigenstate and I locally change my wave function, say by applying some operator to it, then it's not quite so bad. I only get logarithmic growth in the entanglement now rather than linear. Yeah, okay. So another way of seeing why all of this entanglement is spurious is that I've got a thermal correlation length, which is usually very short. So the entanglement entropy, the quantum entanglement entropy is much bigger than the thermal entanglement entropy at some finite temperature. And managing this spurious entanglement is a current research area. There's an interesting paper from Luca Tagliapozzo, actually a student of Murray Clemens, that a good way of doing it is to remove these kind of fast degrees of freedom, kind of like long-range entanglement, which is moving very quickly, but it is actually spurious. You can also think, well, if I've got a quantum state, how does that end up turning into something like a classical density matrix? Like, how does it turn from quantum superposition into a mixture? And that's something that my student has been looking at. That kind of hints at some numerical algorithms doing that, not at that stage yet. There's many other works recently. So I'd say this is something that at the moment is very embryonic, but in the next few years, I think hopefully there's likely to be some good progress on this, which would be a very welcome development. But at the moment, trying to find, for example, like a thermalized state from just time evolution of some non-equilibrium state is very difficult. You essentially can't do it because you can't do the time evolution for long enough to reach something approximating a steady state. Okay, so how much time have we got? A little bit, that's okay. Okay, so I'll give a little bit of an introduction now to various numerical algorithms. So in every, or almost every calculation we've seen so far, the key step is to calculate time evolution of some wave function that we have represented as a matrix product state. So the key problem here is that this exponential e to the minus iht is a pretty crazy complicated object. In some situation where it was really simple, then we probably don't even need to do numerics. We can just calculate this. But in general, there's no easy way of even writing down what this operator looks like. It's just a crazy operator. So what we do is we need some approximation for very small time steps. So if I replace my full time evolution to time t with iterating the time evolution over some small delta t. Okay, and the idea being that if delta t is very small, I can do some kind of expansion here of the exponential and approximate it for some small time step. So essentially, the different ways of doing time evolution correspond to different ways of approximating this exponential acting on my state. So one of the simpler ways is this so-called time evolution block decimation algorithm. This is a perfect example of a matrix product state algorithm. It was actually done independently of DMRG. So I think the history of this is that Dufresne gave a lecture somewhere, maybe Caltech, and I think Steve White, and probably at independent separate times, I think Steve White was in the audience, and then Uli Scholberg was in the audience at some other talk, and they both realized, hey, this is very similar to what we're doing in DMRG. So this was really one of the key steps that actually led to this unification between DMRG and matrix product states. Okay, yeah, history. But the idea is that if my Hamiltonian is short range, so by short range, basically I mean if it's nearest neighbor interaction or nearest neighbor tunneling, then I can decompose it into two-body gates. So the idea is this Suzuki-Trotter decomposition or Lie-Trotter decomposition. It's the same thing. If I can write my Hamiltonian as the sum of two parts, this is a very general theorem. If I can write it as a sum of two parts, H1 plus H2, then I can approximate time evolution operator up to time t of my full Hamiltonian. I can approximate that by repeated iterations, iterate n times of the time evolution of a small time step of H1, followed by, again, a time evolution of a small time step of H2. And I do this n times. So H1, H2, H1, H2, and so on. So the idea now is that if this H1, for example, is a sum of terms that all mutually commute. So the typical example is, say, if I choose H1 to be all terms that exist only on the odd bonds of my system. But because these terms here are all independent, they commute with each other. So that means I can replace my exponential of e to the minus I H1 with the product of each two-body gate, essentially. And then likewise, my H2 would be the terms on all of the even bonds. So instead of bonds 1, 3, 5, it's now bonds 2, 4, and 6, and so on. So the sum H1, H2, H1 plus H2 is my full Hamiltonian, but I've decomposed it into even bonds and odd bonds. So once we do that, then we get some tensor network that looks like this. So we've got the odd bonds, so H1, even bonds, H2, and H1, H2, H1, H2, and so on. So this is in fact, literally, this is a quantum circuit. So we can essentially simulate that on our computer. The basic idea is that we apply, it's very similar to the kind of operations that Charmin was talking about yesterday. So we have we extract two sites of our tensor network. We apply the two-body gate to that. We get then the Fourier-index tensor, and we do an SVD to write it back as a matrix product state of this three-index tensors. There's a lot of details hidden behind that, especially how do we go from this particular SVD here. If you look at the direction of these arrows, well, I didn't put the arrows in here, but they've got arrows that are pointing in that way and in that way. This is actually not quite how we want it when we move around and do the different bonds. So we need to manipulate the directions of those arrows. And doing that is a little complicated, but still, it is probably the simplest MPS algorithm to implement. So maybe, I don't know, I'm guessing 20 lines of Python, but maybe less. Probably like one line of Perl if you use Perl. Yeah, okay. So there's variants of this algorithm for finite size systems, or if it's infinite translation invariant, there's another algorithm that uses that translation invariant symmetry. So we only need to represent two of these sites of my system. So essentially what we do is we've got the A and the B, we apply the gate that way, we kind of conceptually shift it now by one site. So we go B and A, and then apply the gate in the other direction, even bonds and odd bonds. There's essentially two sources of error for this. So there's the discretization error that comes from the Suzuki-Trotter decomposition. So that's also like a finite time step error. For some reason, that became known as the Trotter error. I'm not quite sure why. The Suzuki-Trotter get the decomposition named after him. Trotter gets the error named after him. I'm not sure how he explained that to his mother. But you can do higher order decompositions, for example. So in my code, in the toolkit, the default decomposition is a fourth order one, that instead of having these two slices, even bonds, odd bonds, I think for memory, it's got 11 different slices at various different time steps. Yeah, so the simplest version requires that you invert the singular value matrix. So this one here, I mentioned it a bit briefly. I'm not going to talk in detail about that. But in order to manipulate these isometries, to apply the different gates on the even bonds and odd bonds. Turned out you need to invert this matrix here, which is not very numerically stable because these singular values can decay to 0. But there's actually ways around that. So there's a fix for it, which is this so-called Hastings trick from Matt Hastings, essentially sort of a mathematical physicist. Because it's difficult to do long-range interactions. So this construction here is really quite inherently that it's two-body gates, nearest neighbor, two-body gates. If it's not nearest neighbor, two-body gates, then things get complicated. What you can do, what we do actually do in practice is coarse graining. So I've used this algorithm, for example, to do cylinders, like width 4 cylinders, just coarse grain it until that your interactions become nearest neighbor. That actually works quite well. In principle, you can use swap gates to move lattice sites around. So if you want to do a long-range interaction from here to way over here, I can apply a swap gate, move that lattice site next to it, apply the interaction, swap it back again. We can also imagine using an n-body gate. So rather than a two-body gate, have something that goes longer than that. If you're going to do that, then you're already doing like MPO evolution essentially. So there are better ways than using n-body gates, which I'll talk about very shortly. We might even have time to do that. I haven't run out of slides yet, or I haven't run out of time yet. Okay. Another algorithm is this so-called time-dependent variational principle. So I think the idea of this is apparently due to Dirac. I haven't actually seen the original paper, but if we think, well, if we remember the principle of least action from not quite high school physics, but certainly undergraduate physics, then it says that our variation of the action is 0, which is the time integral of our Lagrangian, which we can write for a quantum system in this form here. So the Euler-Lagrange equations applied to that Lagrangian gives us the time-dependent Schrodinger equation. But actually what we want to do instead is we want to parameterize our wave function. So for our matrix product state, the wave function is actually parameterized by the matrix elements of our tensor, of these A matrices, so-called A matrices. So then the key quantity is then the derivative of our wave function with respect to these matrix elements. So I can take, if I write down an MPS, there's a general prescription that if I have an arbitrary tensor network, but I can take a derivative of that tensor network with respect to one of the matrix elements of the tensor. And the way that you do that is essentially you take that tensor, you want to take the derivative of it, just simply pull it out, remove it from the tensor network. And then you have like more, that gives you an additional set of open legs. And those open legs then give you those extra degrees of freedom are exactly the derivatives of that. So if we take, like say, the derivative with respect to the nth site of my lattice, then I get like an object here that has additional open legs corresponding to the I index, the J index, and the local degree of freedom of that. It looks kind of like a little bit weird written in that form. It actually makes a bit more sense if I parameterize that by more tensors. So this is the tangent space of the MPS. So I think of my MPS as some complicated manifold of all of my variables, or all of my matrix elements. This is the tangent space that corresponds to taking some derivative at some particular point. So it's much better actually if you parameterize it. So for example, if you parameterize it by the set of matrices B. So there's one set of B matrices for every site of my lattice. So I can write down my tangent space of my A matrices of my MPS with respect to B here. And so you can think of this now as my sum. So it's a sum over all possible sites of my Bs, or all possible tensors in my network. There's a different B for each site of my lattice. So the tangent space so this is now what's known as the tangent space of this fixed bond dimension D MPS here. If we go back and look now at our excitation ansatz, in fact, the excited state that we talked about earlier, in fact, is a state vector of this tangent space. The excited state, if we remember before, that was just a sum of all possible translations of, say, the S plus operator acting on every site. That is just an example of this, where my B operator corresponds to my local perturbation. So in general, the TDVP, or this idea of the tangent space, is actually a very general notion. So you can just now think of this tangent space is a space of all possible directions, and we can use that to construct all sorts of algorithms. For example, as an alternative to doing DMRG, you can imagine that we're just going to minimize, with respect to my A matrix elements, the expectation value of the Hamiltonian. And so then if we do that minimum, I calculate the derivatives with respect to A, then I'll get exactly these tangent directions as my gradient vectors of the way I should go in order to minimize that. So that would give you essentially some kind of gradient method. In practice, there's no real advantage to that compared with DMRG, but in principle, you can do this, and people have done these calculations. Okay. But the most commonly used version, I think, is to apply this to time evolution. So if you apply this to time evolution, then we go back to our Lagrangian, and we take the variations now with respect to our A matrix elements. What we get is a version of the time-dependent Schrodinger equation now, which says that the time evolution of my state is projected onto the tangent space of H times psi. So the idea now is that we project my Hamiltonian applied to my state onto the tangent space, and then we integrate it. So, for example, using Runge-Kutta. And there's quite a few different variants of this TDVP, which basically arise from different ways of constructing this projector here. How do you actually project this onto the tangent space? So there's sort of a picture here. I stole this one from Lawrence van der Straten. So you can think of this manifold of fixed bond dimension MPS as this sort of very, very complicated sort of manifold with complicated surface. And then there's tangent planes, some plane that touches my MPS at some point here, but it's orthogonal to that. So it gives me, so as I move in small increments along my tangent space, I'm moving around in my manifold of fixed bond dimension matrix product states. Okay, so some issues with the TDVP idea. So we're doing time evolution in the manifold of this fixed bond dimension MPS, but we've seen before that when you do time evolution, the entropy increases. So we expect the bond dimension should increase as well. But it actually doesn't in the original TDVP algorithm. That's actually a big problem. A simple way around it is that instead of constructing the variations with respect to a single site, I do it with respect to, say, two sites of my system. Like, say, sort of coarse-grained, two sites into one, then I've got a larger space, and then that lets me increase the bond dimension. So there's more efficient ways of doing it than that, rather than using two sites together. It's actually more efficient to increase the bond dimension a little bit, and it's less expensive than two site variations. So there's a very recent paper on that from Von Delft's group, and actually with my student, we're also working on something similar. So there's a projection error because we're projecting our time evolution operator onto the tangent space of our MPS. That is a projection. We do remove some matrix elements that would take me out of that bond dimension D MPS. that projection error is actually hard to measure in the end. So that's a disadvantage of this method. A big advantage of it, though, is that there's no truncation error. So I didn't talk about it much when we did the TEBD, but when you do this singular value decomposition here, I think as Charmin talked a bit about yesterday, in practice, we need to do a truncation of the singular values at this point here. And you can relate that to a loss of fidelity of your wave function. In the TDVP, because it's acting in a fixed bond dimension MPS, there's no truncation error. Or in some versions of it, there's a very small truncation error. So if you do this two-site variations, then you need to do a truncation. And really the key advantage of this TDVP is that in principle, this is a symplectic operator, meaning that it conserves the energy exactly. I think in practice, most modern variants of TDVP don't exactly preserve the energy, but it's very, very close. Certainly much more than say TEBD and other algorithms do. So these days, generally, I'd say it's probably the best performing and accurate method. But there are some caveats. So one of them is that it's very difficult to know, to estimate what the errors are that you're doing. So you can certainly fool yourself by doing a time evolution with some fixed bond dimension MPS that's, say, very small. I get very nice looking results, very smooth, but it turns out to be complete nonsense because you're only representing a very small fraction of the entanglement of your state. So you can fall into traps that you wouldn't fall into with other methods. Play just time. So the final algorithm I'm going to talk about is this so-called Krylov algorithms. So in general, we've got this notion of this Krylov space, which is the space that you get if I start from some initial state. This is a very general linear algebra. It's not even directly MPS or anything. If I just start from some initial vector and I say, well, what space do I get by repeatedly applying my Hamiltonian to that operator? If I do that like k times, then I'll get k different vectors, and the span of those gives me a k-dimensional subspace. One way of generating this subspace, for example, is the Lanczos recurrence relation. So there's a theorem that says that if my operator here is Hermitian, then I can actually get away with, I can actually make an orthogonal subspace of my Krylov vectors just from a two-term recurrence relation. So if there are formulas for the alpha n and the beta n, so I don't need to orthogonalize my vectors against every previous vector. It actually works fine to orthogonalize them against the previous two. So this is good because the computational cost now is essentially constant as my Krylov space grows. Okay, so once I've calculated my Krylov subspace, I can write down the matrix elements of my Hamiltonian in this projected space. And in fact, it's just a tridiagonal matrix of these alphas and these betas that we have here. So then we can calculate a time evolution of this. So essentially what I do now is this is just a matrix. It's a k by k matrix, or well, actually k plus 1, I guess. K plus 1 by k plus 1 matrix. I just calculate the matrix exponential of that matrix. So in practice, like maybe k equals anything from 4 to maybe 20 or so in a real calculation. So I do my, I construct my time evolution operator in this Krylov subspace. My initial state in this subspace is just psi naught. So it's like the vector 1, 0, 0, 0. And then that gives me the expansion coefficients of my Krylov vectors. So this applies directly into the MPS form that if all of these Krylov vectors are separate matrix product states, then by doing sort of MPS arithmetic operations, I can construct a time evolved state. So yeah, so what we need to do there is we need to be able to add two MPS together. I need to scale my MPS by the two factors. I need to truncate them, control the bond dimension, and so on. So there's a little bit of infrastructure we need, but once we've got that, then it's a very flexible kind of procedure. Okay. So in practice, it's actually a little bit complicated that we need to truncate these Krylov vectors. Otherwise, every time we apply the Hamiltonian, the bond dimension of my MPS explodes. But I need to truncate. Once I truncate, then I lose orthogonality. Right. So this Lakeshus procedure breaks down because I've got finite precision. So I lose orthogonality. So you need to choose very carefully the size of the Krylov subspace K. You need to choose the time step. But they are controllable. With some effort, they're controllable. So, for example, you can use a singular value cutoff to control the accuracy of your Krylov vectors. And you can relate that singular value cutoff to the accuracy that you want for your final time-evolved state. In the Krylov sequence, there's a remainder term of this exponential that you can use to determine what value of K you need, of how big your Krylov sequence should be. So actually, in the end, if you're very careful with this, it's actually possible with this method to put a rigorous bound on the error of your time-evolved wave function, which is really nice. I don't think there's any other algorithm that lets you do that. Maybe TUVD if you're very careful to calculate all of the sources of error. A problem with the Krylov algorithm, though, is it only applies to finite systems. So if you apply this Hamiltonian to an infinite system, you get something which is not in this manifold of fixed bond dimension MPS. It's a very technical point, but the bottom line is that the infinite systems, there's no Krylov. So it can be very accurate if you control all of these errors, but it's also very slow because just to do one time step, I need to construct this sequence of MPS, scale them, add them up, truncate them, and so on. So in practice, it's very slow.
Question.
Yeah.
So I think you also can, like the size of the Krylov space is actually also one of the important parts.
Right. Yes.
So how to estimate the error correspond to that? Is it control?
Yeah. So there's a remainder term of the Krylov expansion of the exponential operator. Yeah. It's like the remainder term of a Taylor series expansion. So you can bound, you can put a bound on the bit that's missing.
I see. Another question is that you mentioned that the loops of orthogonality. So does that mean you need to re-orthogonalize as you evolve it? So as time evolve more, I need to re-orthogonalize it more and more.
Yeah, actually, so in practice, what I do is that instead of just calculating this tridiagonal matrix here, I actually calculate all of the matrix elements of this Hamiltonian, and then also all of the overlap. So I've got the identity operator or the effective identity operator, which is not just trivial on the diagonal, and then from those two, then you can do the exact time evolution. Yeah. But an alternative would be do some sort of more exact reorthogonalization of every step. But doing the reorthogonalization in the space of MPS was actually horrible. So I think probably just calculating all of these. So the effect of having the non-orthogonal basis is that these off-diagonal matrix elements are not zero, and just calculate them. Yeah. Right. Yeah. Yeah. So in practice, if you try to as you increase the time step, the Krylov sequence size grows very, very quickly. And once it gets bigger than about 20 or so, then this method just becomes a bit unworkable. So in fact, what we do in the code is that we have a maximum size of the Krylov sequence. If it wants to go bigger than that, then I do an adaptive time step. I say, okay, well, I'm going to split my time step in half. I'm going to do that as two steps. So that's controllable again by looking at this remainder term of the Krylov sequence. Okay, we're just about out of time, and I'm just about at the end of the slide. Okay, there's one more method. I'd almost forgotten this. Yeah, so We talked a bit about if we wanted to do TDVP with a model with long-range interactions, one way of doing that would be to have some larger gate, like some n-body gate. That's actually a little bit crazy. I think you'd be nuts to do TDVP like that. But there is actually a better way if we just think very, very generally. If I write down just a generic MPO, how do I optimize that MPO to best represent my time evolution operator? So conceptually, one way of doing that would just be to write down an arbitrary MPO. So just ABCD, find the ABCD that contains as many terms as possible from the Taylor series expansion by exponential. In practice, I think you don't want to do this by hand, but there are various schemes of how to do that. And this turns out to be closely related to what's known as cluster expansions of the exponential. So the key problem here as to why this exponential is hard is that when you've got terms in your exponential that overlap with each other. So a simple case, if we imagine that we have a Hamiltonian that is purely local, like there's only terms that act on a single side of my lattice. So there's no Hamiltonian that actually does that in practice. But if you imagine, say, it just looks like a sum of say SZ, for example, just a magnetic field. I've turned off everything else. Everything's purely local. I can calculate the exponential of that exactly, because it's just the product of the exponentials on every site. So if there's no overlapping matrix elements, then the exponential is exact. If I've only got overlapping matrix elements that are just nearest neighbor, then I can imagine doing an expansion where I've got, well, the lowest term of the expansion is just the product of those two-body gates, which is a bit like TBD. Now I can imagine I've got higher order terms in my exponential that look like a two-body gate here, overlapping with a two-body gate on the immediately shifted by one side. Okay. A higher order term would be like a product of three of these, one here, another one here, and so on. So that is an expansion parameter that I can truncate. I can say, well, okay, look, I don't care about the fourth order overlapping terms, for example, but I can include all of the other ones, because terms that don't overlap, they decompose. I can write them as an independent product. So actually, it turns out there's a nice way to at least second order, third order, fourth order, maybe. You can do this sort of mechanically. That I think Chung didn't really talk about MPOs, but you can take my word for it. This is like a generic MPO for a Hamiltonian, given like these matrix elements here, CDAB. You can actually write down a second order decomposition that only has a slightly increased bond dimension. And there's a rule for that. So tau here is my time step. And there's actually more complicated variants that include higher order terms and sort of compress the bond dimension. But this actually turned out to be quite efficient. So there's this paper here. Should say, yeah, there's an earlier effort from Mark Zalatel, actually. So when he was a student of Frank Coleman, came up with a scheme for this. And there's a recent paper, it will appear in Cyclo's Physics fairly soon. It's just currently undergoing another round of refereeing. And yeah, that contains all of these details of how to do this. So I'd say this is very new, but it's actually, I think, a quite competitive way of doing the time evolution. The key point here is that this MPO for the Hamiltonian can include long-range terms as well. There's no restriction at all. This is a very general. Every Hamiltonian you can actually write in this form here.
I guess it is like for two-body terms.
No. It can be anything you want. Three-body terms, n-body terms, if you want. Yep. So what would happen in that case is that this is like a block decomposition. So these components here of the MPO would actually get themselves quite big dimensions. But that's maybe manageable.
Is it exactly the second order, or is still some?
Yes, it's exactly the second order. It also includes Actually, there's a more complicated one up here, but it's the same bond dimension, but it didn't fit because it didn't fit on the slide. It's too many terms. But you can actually include some higher order terms as well for the same bond dimension. But it's exact to second order here.
How hard to, the bond dimension just equals 1.
No, it increases faster than that. And actually hidden in here, this is actually like a direct product. So if this is already a large Hamiltonian, this one's actually bigger. It's not just +1. There's some details hidden, but it's manageable. Certainly, second order is quite manageable. Yeah.
It's a direct sum.
No, it's a direct product.
Direct product.
Yeah. Yeah, because this corresponds to all of like the kind of like overlapping terms here. You can compress it, so in practice it's not likely to be that big. But as well for the Ising model, for example, this A is actually like 0. So that's a case where it's particularly easy. Yeah. Anyway, we're more or less out of time. I'm more or less at the end of the slides as well. Yeah, so this is the kind of idea here that once we have this MPO approximation to my time evolution operator, then we just construct the time evolved state by applying the MPO and then compressing it. That's in principle quite stable and quite efficient. Now one issue is here that this operator is not exactly unitary, but it's not far from being unitary. So that's controllable. And yeah, I'll probably finish up here. So that's, yeah, I'll just leave the summary slide. So I'd say rather than implementing your own, or maybe the TBD is not hard to implement on your own, but even if you do that, I'd just do it as an example. So all of these codes include at least one of these algorithms. I think all of these ones here include at least 2 of them. I'm not sure that side 10 that's got TBD. I'm not sure that, does it have any others? You have TDBP. Okay. Yes, good. Yeah, so all of these libraries include at least TDBD and TDBP. The MBS kit, I think, includes MPO. I'm not sure how many include McCulloch. Mine does, but it's quite old by now. Anyway, yeah. And thanks to Jesse Osborne, especially, so he did the excitation ansatz and the wave packet time evolution calculations in here. Many other people that I've worked with to develop these algorithms. So yeah, thank you. I'll leave it there.
Time for questions.
I wonder, you mentioned that the Krylov algorithm is more accurate and but slow. I wonder if compared to TBP, which will be accurate and
yeah, that's a good question. So I think one of the advantages of this Krylov is that it takes some effort, but you can actually control it very precisely. So in the code, what we have is the input is that you tell it what is the maximum fidelity loss you want per time step or per unit time. So it's very controllable in that sense. TDBP is not controllable in that way. In particular, this projection error is like kind of hard to quantify. I think really about the only way to do that is do the calculation again with a larger bond dimension and see how different it is. So we've never done a sort of a real comparison in accuracy between these approaches. But I'd say probably in practice, it might even work out that some kind of hybrid method is the best. So there's actually a paper from, what's the guy's name? Working with Steve White on using Krylov to expand the bond dimension, but do the actual time evolution algorithm using TDVP. And that is probably a very good way to do that. So once you construct your Krylov sequence, that gives you the manifold of, that gives you the directions that you want to look at. And then you construct the time evolution operator in that fixed space of your Krylov vectors. And that would avoid, for example, having this truncation error. So some kind of hybrid method between TDVP and some other scheme, I think, might turn out to be really good. But that's future work.
If one looking for a long time, you will for large system size, then what is cycle means if I do the long time on some error rate, where one should stop, is how many states one should consider, is how it is reliable.
Right, so when you do long time evolution, what's going to happen is that the entanglement will grow very quickly. Now it may be, and certainly people have tend to do these calculations, is to use TDVP with a fixed bond dimension. Now the effect of this is hard to quantify. You can kind of argue that in nature what's going to happen is that your system decoheres and the entanglement kind of stays finite. I think that's probably not a very weak argument. And I don't think you can make any direct connection with like the reduction in entropy you get from, say, finite bond dimension. You can't really associate that with any particular physical dissipative process. So I think that's actually a big question mark as to how do you best do long time evolution and control the bond dimension.
That can finite scaling can work.
Sorry?
Finite scaling, if I start with small system,
right,
that will be very accurate.
Yeah.
And then if I increase the system size and do the scaling.
Yeah, you can. So I'm not sure that helps a lot though, because what's going to happen is that the entanglement will increase until you get to a volume law scaling. And once you do that, then your MDS bond dimension is already, it's essentially doing exact organization at that point, because your MPS bond dimension is exponentially big in your system size. So I'm not sure that finite size scaling actually tells you very much for these time evolution calculations. You could just do time evolution of a larger system and just look at observables in some small region of it. Because in the end, time evolution is local. The algorithms don't look so much like it. Well, actually, I think TUBD basically sort of emphasizes this, that you do the time evolution just by applying very local gates. So in practice, what happens here is that you've got these many body correlations that are kind of spreading out through your system. Sort of, you can think of it sort of coming at these angles in the space-time diagram. And the size of your system doesn't matter too much. You just get, as you evolve it for longer and longer and longer, you just get more and more correlations coming in from longer distances. And so whether you do time evolution on a small system, for some fixed time, whether it's a small system or a big system really doesn't matter, because everything's local. Not local anyway.
If one want to do two-dimensional time evolution, so I think there's something one could work.
Right. So all of these methods are kind of inherently one-dimensional. So you can attempt to do 2D by wrapping it, like sort of unrolling it. So we do, for example, we do a lot looking at cylinders. But in that case, the length of the cylinder is essentially arbitrary. It could be infinite quite commonly, but the width of the cylinder, essentially pretty much all of these algorithms are exponentially difficult with respect to the width. And the same is true of the time evolution. But as long as the width isn't too big, then it's manageable. So like maybe width 6, 8 is not too bad. Width 10 usually is is about where it gets very, very hard.
In the PDBT, at least we have 3 errors come from the SVD configuration, and the explanation we use the latest iteration, and the factor error. So there's 3 errors generated from this algorithm. Is there any stable strategy that we can adopt to get a correct MDS for this kind of
Yeah, so what you need to do then is systematically go through every error and try and quantify that. So for example, with trotter errors, you can estimate what these are, like from the order of the decomposition, and you can put some bound on what the error is. And in the other cases, you just need to go through. Yeah, there's no like sort of one size fits all prescription. This will be the error. You just need to go through systematically each source of the error and try and find some bound on it. I think for the projection error in the TDVP, for example, that's quite hard to estimate what this is in practice. In the TUVD, for example, you can calculate, or at least you know at least up to some order as to how big these errors are, depending on which decomposition you use. So in the TUVD, for example, it's a trade-off between the trotter error from the discretization of the time step here and the truncation error. That if you can think, okay, well I can reduce my time step to reduce the error from this decomposition, but if we do that, then I'm truncating many more times. So that's bad. If I go the other way, if I get a very large time step, then my truncation error is smaller, but I start to get big errors from the Suzuki trotter decomposition. So in practice, actually, if you want to minimize that, I think you just have to actually plot, what is the error as a function of my time step. And in TUVD, you see that it starts off. So if you look at the error as a function of say delta t, then it's very big for small delta t because you're doing lots of truncations. It has some optimal point, and then it gets very big again where it's dominated by the trotter error. And then this is truncation. Yeah, so if you really want to optimize everything, then you can actually construct that plot, and then you just want to make sure that you're sitting somewhere down here where your error is minimized.
That's error.
So one way of doing it would be, say, the fidelity. So yeah, you'd need to do like a benchmark calculation that's like the most accurate possible you can do, and then you do say like with a higher order decomposition, and then do it again with the actual algorithm you would use, and look at measure the fidelity. Yeah. So if you're unable to do that, if you're unable to get a good benchmark calculation to compare fidelity or something like that, then I think it's more difficult. You need to use some theoretical error bounds and so on. But theoretical error bounds are usually quite different to the error you get in practice.
This page is common that actually you want to employ SVT, so I think right moment that you have the TV method based on QR and very small.
Right.
They can do that.
Yeah, I mean, you need to do an SVD if you're actually going to truncate your bond dimension. But yeah, there are ways of avoiding that, and a lot of the time you can actually get away with doing a QR rather than an SVD. Yeah.
Found that error in TDVP is pretty tricky. If you go to the very large bond dimension limit, then essentially it's should be no trouble.
Right.
So the error are kind of related to each other.
Yeah, yes, I agree. Hard to quantify, which is
potentially have a related question because I mean TDD you kind of know like you know the truncation error, so you know that how accurate you are, but is there a comparison like one-to-one translation because in TDD you don't fix the bound dimension, right? So sometimes you cannot really push the bound dimension too large because it's very complicated, especially the input size. So sometimes you compare like the bound dimension 100 TDD and maybe you only do like 30 bound dimension TDD. So how do you compare this accuracy?
That's a good question. I think really the only reliable way or sort of general way is just to have some benchmark calculation that you tune everything so that you know that it's very accurate. Which of course is fine if it's a simple benchmark calculation. If it's a more complicated case, I think that's really hard. I think that's a potential advantage of this Krylov kind of approach, that everything is controllable, but that's with quite a bit of effort to work out all of these sources of errors. I mean, in principle, you can, so I think that the main problem, I think, with TDBP is this projection error that's hard to quantify. If other cases where you're doing some truncation or something like that, you can estimate the amount that you're truncating and remain a term of some expansion and things like this. You can give some theoretical error bounds, which is useful.
Okay. Due to the time, let's take a break. But since the speaker again, and then we'll take a break for 10 minutes. At 10:35.要做。
就是我一直都想等的，就是 building block 有存在性可以可以。
So yes, could be.
Oh, 那可以用在。
In that case, there's no. Right, so it makes the NTHU slightly whether it makes it more difficult numerically or not depends on what value what matters, because you're not necessarily encoding. You might be, you could be AKLT. Because physically it will depend on what situation you're in. I don't know off the top of my head. Yeah. So I think off the top of my head, I think what happens is that spectral function is actually a little bit weird. I think it's you don't have to move very far away from pi before the single main number disappears. So yeah, I suspect that kind of thing is more difficult. Right, yeah, it's going to be useful. I can also imagine like putting in like a squared or something like that as well. But that wouldn't be an elementary extension, that would be in one thing that would be like single Yes, yes, you can. That's an example of that. The expectations, if you want to calculate a special function, you need to do, like, say, some C-dagger operator, for example. But what we actually show is separate. So the C-dagger half is going to create, also change the spin by half and add +1 particle. So these are actually two different excitations. So what we did is actually you can write the excitation in that such that you decompose this and you just have pure charge and pure spin excitation. So you can also do that to a spin half change, right? With the elementary excitation to spin on have spin half. But if you do a special function all the way, like an S plus operator, changing my spin by +1. But what you can do is yeah, the spin-ons essentially look like some kind of domain board. And so you can write down the extension of that so such that you get a spin rather than spin one. To do the nuts. Yeah. So all of these kind of fractional extensions, yes. Okay.
About the totalization. Is it problem dependent?
Sorry, is the
problem dependent?
Yeah, so the entanglement growth, the slope of this entanglement growth, so it depends very strongly on the problem for sure. Yeah.
Quantum computation. So you cannot use like
right, it's got some arbitrary quantum circuit. Right, yeah, sure. I mean, it's not going to be nearest neighbor, so yeah. Yeah. Right. Yeah.
Applied one problem. So I use the first one. Where is the arrow in the order of 1. And that is time stepping. If I do the long time, then also circuit will be if I do the then there is no topological. I directly solve from the order of error means
Yeah, very much. Yeah. Very strongly dependent. Yeah, so if your system is also inhomogeneous, as it would be in your case, then yeah, anything can happen, right? Because you'll get entanglements to be very much depending on the position where you are in the lattice. So in that case, yeah. So in that case, you want to be very careful. To allow
也还好，对啊，但是这样子今天都只能这样子。应该是有啊，多了的家里边这个是有，应该多200多。对，他们在哪里？他们应该算你那个东西。安总，他是从之前在10号点，然后后来去，他先去那个变好几个哦，然后所以我当时加的，他说然后那个没有水是一样的。然后我是在哪？在东部。而且知道在他没有，但是我在国外用，要不还是要啊，还是把现在不多接。对啊，我这个过程不清楚，对啊，我都刚刚没有人说的。你要两个来，
想说首先这个会计也没有。反正分2张，1张之内。
要说我们
你要把你的家庭的成绩打下去才到分，不要这2个。哎，那个。
因为我有想要吃，就想要跟他们怎么样？
我就把这个词汇
多一点。哎，然后暑假是去打破意大利，我看一下，因为那个时候刚好张老师有提供我一个那个 postdoc 的讯息，在那个也是就是在拿破嘛，在那个什么什么大学 S 开头，意大利的。可是我后来查一下，我们意大利人是啊，跟台湾一样，在欧洲都是。
The topic starting now, we need
对啊，我要加入部，对，然后选刚线2家，因为那个你的对，你也开始要整个，那个我来第一页上面，OK，那我们教好像跟教育部有关的。哦，这个大家，哦，所以今天刚这件事情都比较用。哦，本来要去见人家。哦，我懂。对。
为什么会有讲？
这个不是，这个是，
然后是你自己我的
台的中国了
啊，哦，我也在找 JV 我要少的，没关系，
没有，就是他们
哦，所以我家就不用钱。然后好，我问他，你为什么？然后你说我是可以。
我需要带麦克风吗？
So, we will start our next talk soon. So the next talk will be given by Professor Inzer Gao from National Taiwan University. And so he will introduce, he has a lot of interesting work related to the quantum spin liquid, which is also a very interesting system and very difficult to be, to be simulated or to be targeted by many methods. So this is kind of one of the typical system that we, appears. So yeah, so this is one cool. This is also.
So can people hear me? Turn this on. It's okay?
Yeah, I think so.
Right.
Okay, let's try.
No. Maybe.
Can you hear me?
Try the close to your mouth first.
我大声。
I heard something.
下面一直有。
Yeah.
Okay. Okay. Yeah. Okay.
Yeah, so I got this assignment from Jiaming that I can talk about
liquids. And 对，那个老师你那要那讲，你把自己没，我可说吧，把自己没有了。
I got this assignment from Jiaming that I should talk about quantum spin liquids. And I realized it's a huge task. This is a very big project, field, and there's a lot of things. So I prepared 70 slides. So let's see how far I can go. And that won't cover any, like 1% of the research. Okay, so here's a briefly outline. So I want to introduce a couple of things. So basically, I want to answer.
Yeah.
Okay. So I want to talk about, give you some like a very brief introduction on what is a quantum spin liquid in the traditional manner and in more like modern quantum information era kind of definition. And so that means that we're going to involve some entanglement and discuss some long-range entanglement. And also the spin liquid is closely related to the topological order that I'll also discuss. I'll give you some flavors of the quantum spin liquids and where to look for them and how we process them. So the first question we want to ask is just quantum spin liquid. So I have a poll here. So people who heard about quantum spin liquid, raise your hand. Okay, many people heard about it. Okay, so what is a quantum spin liquid?
Something funky.
Okay, so So the definition, the layman's definition is actually it's a system of spins that is spin liquid, and it's a liquid, so it shouldn't have any like Lorentz order. So basically, it's a spin which has correlated, but this doesn't order at the zero temperature. But if you look at this phase and think for a second, this gives you nothing, right? It doesn't really give you a working definition of what the quantum spin liquid is. So this basically just tell you, okay, what the quantum spin liquid is constant. Okay, you don't have to make any ordering. And it doesn't give you any sense like where to look for it, and it's not interesting. And what's the physics involved in this system? It's not clear. Okay, so after several decades of study, people come to realize that the spin liquid can be defined in this way, at least theoretical. So quantum spin liquid is a state with long-range entanglement. Okay, so this is something that doesn't make sense yet, but what we mean by this is that, okay, so if I give you a state and I want you to tell me if it's a quantum spin liquid, and what you can do is you randomly select some local unitaries and apply to this wave function, and randomly apply this wave function, and see if we can transform this wave function into some product state. Okay. So the meaning of long-range entanglement just means that you cannot do this. You cannot transform this wave function into a product state wave function through a finite times of local unitaries. In a sense that basically it's a state that you cannot deform it without crossing without a gap closing phase transition. What does it mean? It means that, okay, so I have a state, somehow I have some Hamiltonian, I know how to evolve it. And if I can transform this state through certain Hamiltonian and without closing a gap, so basically my spectrum, the ground state and the first decide state, there's no like level crossing. So which means that the property of the state and this state are the same. And if I can transform this state into a product state, and then that means that this state has no long-range entanglement.
Before you proceed that, so we are talking about the quantum spin liquid, but then is there classical spin liquid?
Yes. Okay, so classical spin liquid you can think of is just okay. What I'm gonna tell you can think of some states, superposition of some thermal states, and there's it's not it's a macroscopic degeneracy. But for the quantum spin liquid, we are talking about like a single state, right? Which is the superposition of a lot of classical configurations. That's a good question. I actually, even a classical spin liquid is whole world of okay at once. Okay. So how do we study this? How do we picture this kind of spin liquid states? And Anderson in 1973, when he was trying to study the ground state of a triangular lattice Heisenberg model, so he came up with this idea called the resonance valence bond state. Basically, he argued that the ground state of this triangular lattice Heisenberg model, you can think of this as a superposition of this so-called valence bond. So this oval here is basically a valence bond, which is basically just a singlet. and you cover this triangular lattice with this singlets, and you think of that all these possible coverings, and there's a superposition, all these possible coverings, and you get a quantum wave function. And he argued that this is a liquid state, and it should be at least a very good variational ansatz for the ground state for the triangular lattice Heisenberg model. Okay. So this RVP type of picture is actually, although it later people show that it's not a true ground state of the triangular lattice Heisenberg model, but this picture has been a long-lasting tool for us to think about, at least pictorially and also like theoretical, how to think about quantum spin liquids. Okay, so let's briefly discuss what kind of state. So this is basically just covering, the dimer covering, or the valence bond covering of your lattice. What kind of valence bond states I can have? So in this example, I can cover this with basically my singlets are forming some pattern. So I have a lattice translational symmetry. So this is actually a symmetry breaking state because I break the lattice translational symmetry. And this is called a valence bond solid. So this is not a quantum spin liquid. Okay? So you have a well-defined pattern. If you do a say X-ray scattering or a neutron scattering, then you should see some peak. To get a liquid state, you need to do a lot of shuffling. So basically, you think about all these possible valence bond coverings on this triangular lattice. So this is one classical conversion, another one, and you do some superposition with different weights. And this will give you something called a short range RVP. To create an excitation, we need to break the singlet. So I have to flip one spin in a singlet to become a triplet. So there's a singlet triplet gap. So this is the quantum spin liquid state and with an NH gap. Okay. So my ground state, and there's this first excited state, there's a gap. So here I'm just restricting myself the dimer covering between the side that is nearest neighbor. I can also have something called long range RVP. Okay. So I can have different probability of covering all these different sides. Because of this long range coverings, it's possible to construct gapless excitations out of this ground state. So people have been using this valence bond states as a variational ansatz to study a lot of problems. So you can write down a wave function, and you can for long range RVP, you can write down a wave function with certain like probability of decay, how they form the bonds, and so you can study even just the wave function itself, the behavior, so the correlation of the wave function, building the wave function, and how they behave without control. Okay, but for the following, we're going to focus more on this gap, the spin liquid. Okay. So one day, in this short range RVP, if I break the singlet, so I have two spin ups. So we can study how they correlate. Okay? And in the spin liquid state, so this actually you are free to move spins. So these spins are called deconfined. So their potential is not a linear potential, but there's like a Coulomb-like potential between these two individual spins. So So this is something we can exactly show in 1D. So in 1D, you have this spin 1/2 excitation that's called a spin-off. Say if I have a spin chain, a Heisenberg spin chain or a spin chain, and I create the excitation, so create excitation, I flip one spin. And this flip one spin, the quantum number of this excitation is actually spin 1. It's not spin 1/2, right? Because you coming from spin 0 to spin 1, but the difference is one spin flip. But in quantum spin chain, it can be shown by either Boltzmannization or other methods. We can show that actually spin 1 excitation is not stable, and they can decay into two spin 1/2 excitation called spin-on. And this spin-on, in this case, it's basically just a domain wall between the spins. Okay, and they can propagate. You have a left going and right going. In higher dimensional spin liquids, it's possible. So if you want to move, okay, so let's think that somehow I create a single spin excitation. So normally you cannot redo it. I have to break up a singlet. So I can move one of the spin-ons to very far away. So imagine I can create a spin-on. This spin-on can think of as a defect in this valence bond solid. Okay, and I can move them. So if I have this short range RVB, so which means that my background is fluctuating a lot. So I have my spin can move, my single spin can move around. So I have a well-defined single spin 1/2 excitation. And what's the statistics of this spin-on? So people can model it with fermion, bosons, and this, or even like anyons in 2D. So this spin is already fractionized because it carries spin 1/2 excitation. And what following we'll see a lot of these cases that in spin liquid you can have some excitations. These quasi-particles are not fermion or bosons, at least in 2D. That's what anyons for. Okay, I'm going very fast. So if you have any questions, please start me, because I think I cannot go over all my slides. Otherwise, it will be the information overload. Ask me a question. Okay, so these are look very nice on picture, right? I know how to draw this, but when come to a model, you realize it's actually hard to write down a model for this kind of singlets, right? I can construct a wave function using this RVB as ansatz, but what kind of model I can construct? Because I need a microscopic model so that I can map into, say, like the real materials. But if you look at this, okay, this looks like a dimer covering, right? Because I'm each quantum only covered by each spin is covered by one dimer, okay? And only one dimer in this configuration. So instead of the spin model, people study this called the quantum dimer model. So basically, it's a very simple model. It only has two terms. One is the resonating term. Okay, so if I have a dimer, so I'm squareless. If I have a dimer like this, then I flip. Okay, this term basically just, if I have a dimer copying like this, I just change it to this. And the other term is a diagonal term. It's just the potential energy. Okay. It turns out when J is equal to V, this model is exactly solvable. And the solution, the ground station solution is this so-called RK state. Basically, is the equal weight superposition of all these classical covering dimer covering configurations. Okay, so basically you just do equal weight superposition of all these classical dimer configurations, and you get this. And you can measure the correlation, and it has a parallel correlation. It's a liquid-like state, and this is the so-called RK point. But in this model, it's found that actually only this point is a liquid-like. All these other V over J, there's some kind of translational symmetry breaking. So this is like Poincare valence bond solid, columnar valence bond solid, and it's the stagger valence bond solid. So far from this, away from this point, all the states are actually not liquid-like state. And most Sondi studied this triangle lattice, and they found actually you can stabilize an RVB state in a certain region of the V over J. And so this is a liquid state. Okay, this is short range RVB state. The interesting thing is that if you put this configurations on a torus, there's actually topological degeneracy. Okay, so let's look at this configuration, and I have a cut here. Okay, so number of dimers I cut is 1, right? Along this cut. And I can apply some resonating. Okay, so I can resonate these two dimers. And because of this resonating term, the only configuration I can have is this. And it's n equal to 3. So there are actually 2 topological sectors. Right? According to this cut, I can have an even number of dimers along this cut, or odd number of dimers along this cut, right? Along this direction. So if I put it on cylinder, then I have 2 topological sectors. If I put it on torus, so it means that periodic boundary condition in this direction and this direction, I can define another cut, horizontal cut, and you also have 2 sectors. So I put this configuration on torus. I have 4 different topological sectors. So I can even, even, Okay, so this is sort of like a preliminary of what we're gonna talk in the following. So far, any questions?
We can talk.
So normally, because if you want to change, so it can be any cut because all along these cuts it's all preserved. Okay, you can say, okay, if I do this along this cut, right, and I do resonating, then it's an even set. But I've only cut it once. And also, not sure how to change topological sector in the time. Okay, so I think it will be clear when we talk about torical.
You call it a sector because it cannot be changed by the controller.
Yes.
And how about the excitation? So if we have the single.
Well, I mean, in diamond model, your excitation is you have monomers. Right?
So do we also, I mean, is this sort of the symmetry for all these?
No, because you have to. Because these are degenerate states.
Yeah, probably for.
Station.
So the Hamiltonian does not change this even up. So it's a very different sort of symmetry sector. But what about exciting state? You still have this kind of symmetry. I guess in very high high energy excitation probably doesn't. Great.
Yeah.
I don't know.
I think because okay, so in the dimer model, how do you break? Without introducing monomers, you cannot have excitation.
Yeah. Oh. Okay, so it's only.
So this is a very artificial like model. So I always stay in the sort of like box statement for.
I see.
Without if I introduce monomer, then I should have terms to create another. Okay, so we just saw a case that I can have a well-defined topological order, and this kind of this kind of sectors I have defined with a global or like a car. I cannot, if I look at locally here, I cannot really tell if this is an even or odd sector. So this is one simple example that you have a topological order. So we are more familiar with the so-called all the symmetry breaking or spontaneous symmetry breaking order. So normally, say, the superconductor, then when you go into a superconducting state, then you're basically the potential of the order parameters like this Mexican hat. And then you break the symmetry, break the E1 symmetry in this case. So the Gaussian has less symmetry than Hamiltonian. And this is well defined, described by this Landau-Ginsburg-Wilson type of theory. You have a symmetry breaking, you can define order parameters, local order. But so topological order, you have a degeneracy of the ground state, but this degeneracy actually depends on the topology of where you put your system. For example, if I put the previous one in a cylinder, I can only define one cut. So my degeneracy is 2, but I put on a torus, then it's 4. Okay. So I cannot really have a local order parameter to define this. And the famous example is actually this fractional quantum state. This is the first system that people identify as with a topological order. So let's look at some concrete example. So the first example is very famous. It's especially more famous nowadays because it's related to like one of our superrational. It's called Torrico. The Hamiltonian is very simple. Okay, so the 3 examples I'll give you today, 2 of them are from this paper, okay, from Kitas. This is actually not a hard paper to read compared to like other Kita papers. Okay, so this is actually a very simple Hamiltonian. So I have a spin. Okay. I have a lattice, but my spin lives on the bound of this lattice. I define 2 operators. Okay. So the first operator is called my A operator is called star operator. Okay. My star operator basically operates sigma z on this 4 spins. The other is called a blockade operator. I operate on the 4 spins on this blockade. Okay, so this is basically the vertex operator. Okay. So let's the good thing about this Hamiltonian is that this operator this bucket operator and star operator commutes. They mutually commute and they commute with Hamiltonian. So in the quantum information language, these are called stabilizers. And these are basically you can use this to detect if there's this unwanted excitations that you can do some error correction. So let's take the different limits. So when A goes to infinity, A is much larger than B. And you can see that basically the state will be composed of this kind of red loops, right? So this red loops is basically I pick up a sigma z -1. Okay. So this is my ground state for this kind of loop for when A is much larger. And on the other end, when B is much larger, then my ground state will be composed of this different kind of loops. Okay. So the ground state will be some kind of superposition of all these loop configurations. Okay. And this is the theoretical, and this is actually can be exactly solved. So what's the property of this ground state? Again, we can define the topological sectors. Okay. So I can define, say, I have a white parity. So I basically introduce a string of the sigma z's along the x directions. And so I can detect how many cuts, how many loop crossings I have along this cut. Because each loop crossing will pick up one z, or pick up one -9. Okay? And so depends on the number of cuts I have. I can have a parity even or parity odd. Again, I fulfill the ground state genericity on progress because I can also have defined cut along this direction. But the interesting thing is the excitation. I can define the excitation in this way. I can define excitation. I call electric excitation. Which is say along the okay, so this is my electric excitation. So I can define a Wilson loop operator. So basically a string of sigma z's. Okay. If I have one thing, then basically I basically flip all the spins along the way. But I have an open end like this. Okay. Then I can surround this with this blue loop. Okay. And with a simple calculation, you can convince yourself that in this case, was confusing. You can show that this has excitation and -1. Okay, so we pick up a -1, and so you can have a excitation of K. You also pick up a -1. So these are the excitations at the end of your Wilson strings. Okay, and so every time you want to create an excitation, you create in pairs, but you can move one to the infinity and try to measure the quantum number using the other operator. And also, another interesting thing is that if you can try to wind this to excitations, okay? So if I have an electric excitation and magnetic flux excitation, and I have electric, and they are self-specific. So basically, I have electric excitation and I wind them once. It's a bosonic-like. Okay, so it's bosonic-like. But if I wind an electric excitation and flux excitation, and then this is a fermionic-like. So this is called the fermionic statistics. Okay. And this model can be written in terms of this is as a Z2 gauge structure. So to describe this spin liquid is actually a Z2. So this is a Z2 spin liquid, and you can also tell from the number of anneal excitations. There's a vacuum, and there's an E, and there's an M, and there's a bound state of E and M. So this is basically give you a full excitations. And this is the character for Z2 spin liquid. To kind of understand this, so if you have a spin liquid, at least for the Z2 spin liquid, you can think of it there's like a spaghetti of loops in the background. And if you have a very sparse loops, and then if I can create a pair of excitations, say the spin-ons or the electric excitations in my previous language, it's actually hard to move things around. So there will be a linear potential between these two excitations, and so they are bounded. So it's almost impossible to separate them. Normally, this leads to the Mengele state, but in a quantum spin liquid, then you have these fluctuation loops, and then you are free to move these fractionized excitations around, and so these are deconfined. And this is sort of like a signature of your quantum spin liquid. Okay, so yeah, so far any questions? So I'm going very quickly. So another important thing is, how do I describe this kind of state? The one important aspect coming from the quantum information is this entanglement. I think I'm not sure if Chung introduced this entanglement entropy yesterday. So if we have two subsystems, A and B, I can define a subsystem density matrix, basically the full density matrix of the whole system, and I trace out that the A part of degrees of freedom, I get this density matrix. And using this density matrix, I can construct the polynomial entanglement entropy between these two regions. Okay? For a lot of the Hamiltonian we study, if you have a gap Hamiltonian, there is something called the entanglement area law. So basically, this tells you that the entanglement entropy between these two regions scales as the boundary of the system. Okay. So the volume is the full block, and area is the boundary. So it's called area of the boundary law. Okay. You have this kind of scale. So we can take a simple example. Let me say if I have two spin system, right? So I have a spin A and B, and I have some way to control the mixing between these product states. So I can trace out, I can use this, right? So this is my cat. I can use the broad and I construct a density matrix and then trace out say B. Okay. So this will be my density matrix. And I plug this into the previous equation, I get my von Neumann entropy this way. And so we see that when the system, say the phi is 0, which means phi is 0, this guy is 0, this has a product state. So basically subregion A and subregion B is separable. So the entanglement entropy is 0. But if I have the maximal integral state, so I have a singlet here, right? So the entanglement entropy is square root of 2. Okay. So we can look at some examples for the entanglement in 1D. So for the gap system, 1D example is the AKLT like a state. So basically, you can write it in terms of this band bond, basically. Okay, so if I cut this intake, so these are singlets, short-range singlets. So if I cut here, I have entanglement entropy of log 2. Cut here, entanglement entropy of log 2. Okay. Oh, sorry. This should be log 2. So my entanglement entropy is actually constant. But if I have, say, like a gapless or critical state, say in 1D Heisenberg model, then my ground state actually is the long range singlet. Superposition of long range singlets. So I can try to count the number of singlets going through this cut. Okay. 1, 2, 3, 4. So if you do this counting, actually, you'll find that this entanglement entropy depends on log of this system size, subsystem size, and also this prefactor. And this prefactor is actually related to the central charge, proportional here. So this entanglement entropy is proportional to the central charge of the corresponding CFT describing this gapless system. Okay. So the entanglement in 2D, we can sort of use in the same way, and let's use also the sort of like a short-range singlet. Okay. So if I try to cut this here, okay, so each one, remember each singlet I have a log 2, right? So I'm only cutting here 1, 2, 3, 4. So I have 6. Okay, I cut through 6 singlets. But entanglement entropy is 6 times log 2. So if I enlarge this, so I'm cutting through like again 8 because. So my entanglement entropy is actually proportional to this boundary. Okay, so this is sort of like a simplest way to understand this entanglement entropy at level. But remember, yeah.
So this is not the specific state, it's just a particular state.
Yeah, the gap state, so it is dependent on solid, basically. I'm going to talk about it in this state. So remember, we said, okay, you can describe this gap spin liquid state in terms of some like the superposition of loops, right? And this loops actually constrain how many configuration I can, if I have a boundary here, I can cross this boundary. Right? So So in for the gap system in 2D, there's the entanglement entropy. In addition to this area loss piece, there's additive terms. This term is actually related to the what kind of excitations you have in this topological order state. Okay? So for spin Z2 spin liquid, this additive term correction is minus log 2. Okay. Notice this is a minus term. So basically, topological order decrease the entanglement. So the symptom will go into the minimum entanglement state. How do I understand this? Okay, so I remember I told you the spin liquid state, Z2 liquid state is some kind of loops. Okay. Across the boundary. So the loop structure actually impose some constraints. You can the subsystem can cross this boundary. Okay. So a simple counting is instead of just the area, because you have a constraint, you get this 2 to the L minus 1 because of the constraint, and so you get a gamma log 2. And so this is sort of a hand waving way of saying this, but you can get this exact number from the topological quantum field theory. There are experts who do this. Okay, from TQFT, then you can get, actually this gamma is related to this so-called quantum dimensions, or sum of the quantum dimensions. So the quantum dimensions counts the quantum dimension for each excitations. Okay? So in the torical case, or in the Z2 spin liquid case, each excitation has the quantum dimension 1. So these are the flux, electric flux and fermion excitations we describe in this torical case, and their quantum dimensions are each is 1. So you do this sum, you get the log 2. So if you have like icing anyons, the excitation has this quantum dimension is golden ratio, and so you have the value of gamma.
But how do you plot this quantum dimension? How do you measure quantum dimension? Always analytical correlation.
Well, numerically, you can only measure this.
There's like no way to directly.
It's like CFT, you have a central charge. Yes. And it's kind of, you have a dictionary of trying to measure. I don't know if that, can you correctly measure this? Well, you can measure excitation, but.
Yeah, maybe. I mean, it's kind of like the number of degrees of freedom with the excitation, but then if it's fractional, I'm not sure exactly how.
Yeah.
How you do that.
Okay. So the generic model, I think it will be very difficult because the state will be very complicated. We want to assess that very.
No, I mean, numerical is you can
get gamma. Yeah,
but you have to know the underlying theory structure of your wave function to really know this. And if you look at this, these two numbers are actually very close, right? But I guess you can tell because in a sense,
you can try to see how many sectors you have, right?
You can create a single excitation, try to wind them. But I know how to do this in the Z2 case because you can do transfer matrix with quantum numbers. All the anyons.
I have no idea.
Yeah, I mean, there's probably a way from the people mentioned the Hilbert space. Yes.
Yeah, but that's a good question. Okay. So in practice, how do you measure this this gamma here? Okay. So remember, when you measure the entanglement entropy between two regions, you always have this area law term. So to really get this gamma, you want to subtract of all these area law contributions. And there are two clever proposals to do this. I'm plotting here is the proposal by Kita and Presto. The way they do it, you can think about computing the entanglement entropy for region ABC. Okay, so ABC, there's a boundary here with D. So you have to trace out D, right? So you compute a reduced density matrix of this. And then you compute a reduced density matrix of SAB, SBC, SAC. There's a minus sign here, and add SAA, SB, and C. Okay. Why do this? Okay. So let's look at this R here. So this R belongs to SABC, right? This boundary. When you compute SABC, this is the boundary you get. And also it's a boundary for SAB, and it's also a boundary for SAC. Right? SAC also includes this boundary. And you also have a boundary for SA. So you have positive contribution from here. So for this boundary, you have a positive contribution from here, positive contribution from here, and two negative contribution from here. So for this area term, anything linear to this boundary is subtracted, right? And so each piece will contribute to a gamma. So you have yeah. So you can then subtract them off, and then you get, by doing this subtraction, you get this gamma, right? So you can look at, say, this boundary here, right? This boundary, when I calculate the SA, has this boundary. When I calculate SAC, has this boundary. And yeah. So I basically subtract them off. This boundary is subtracted off. So by doing this, I can get the entanglement, just get it, subtract all the area law terms and get the entanglement. Also, if you do on a cylinder, you can just do on the cut. Okay. So this is one example. People use DMRG to compute a torical. And so the torical phase diagram is that if you apply a field along this direction, you come from a topological phase to some topological trivial phase. So this, yeah.
So
I think this calculation is not wrong. It's not right. It shouldn't be log 2 on the cylinder.
yeah. So
by the way, this is Chung's.
Yeah, no, that's right.
Yeah. Okay. Anyway,
it looks like a forest.
Yeah. Okay. So let's forget about the number here. Basically, if you have a non-topological trivial state, then your intercept should be 0 because you don't have this gamma term here. Then if you have some negative intercept, then you have this topological state. So it means that this is in a topological state. So this is in practice how you compute this. I think this state not converged, -1. You also
the topological order does have an effect on entropy.
Entanglement entropy.
Yeah, entanglement entropy to reduce the entropy. In the entanglement, I think entanglement entropy is still a kind of entropy, right?
Yes.
And would this scenario apply to the all topological materials, which means that in principle the material with topological order would have lower entropy than the topological trivial matter.
Well, I mean, you're talking about thermal entropies.
I'm talking about the real matter.
Yeah, but the real matter depends on, because if you have a topological insulator.
For example, the topological order from the band structure.
But that's actually topological trivial. It's a symmetry protected topological state.
Yeah.
So it's not really this topological. It has a short entanglement. So which means that you can, if you don't preserve the symmetry of the system, you can be linked to a product state. So this is topological insulator and all this so-called topological
still topological trivial.
This topological trivial.
In this
case. They don't have a long-range entanglement.
This statement is true for all the protocol orders.
You mean this statement or which statement?
I mean, you always say topological entropy with negative topological.
Yeah. So for gapped.
Forget this is
how much time do I have?
15.
I'll fly through this. This is another. Okay. So another way to introduce a model is this. So you can introduce some kind of frustration. So basically, this model is the canonical model. So basically, it depends on the interaction depends on the direction of the bond. So I've defined this x, and this is the xx, and y, z. So this interaction actually is frustrating, although it just looks like a very simple icing type of interaction of the bonds. And so if you tune the interaction strength, and you get this kind of phase diagram. When one of the j is very large, you have an absorption limit, and you have a gap spin liquid, and actually this can be connected to the torical case that we studied, we described. And when all the j's are the same, the system is in this at this point, and this describes a gapless spin liquid state. And this actually exactly solvable. You can introduce formal runners on each lattice side. Okay. I won't go through the details of how to solve this. Then you'll find that it turns out that, okay, you are left with one sigma runner living on here. And it actually has a band structure like a graphene, and it has Dirac points near K and K prime. So the ground state, of the system is actually you can define a flux in each blockade, and the ground state is all these blockades have zero flux, and to create a flux excitation, there's a gap. Okay, so you have a gapped excitation on this sector, but you have a gapless excitation for this boundary runner. So the way to create an excitation is basically introduce a pi flux on one of the pockets, and this it can be related to what we discussed previously, the magnetic, the flux excitation, or called the Bison excitation.
But this is similar to the topological insulator, we call it trivial, that similar that it has a bulk gap, energy gap, but have the surface state.
No, but this is different because I have these are the fractionalized excitations. These are Maronas. They're not like electronic excitations. Mm-hmm. So this is I fractionalized.
Oh, this already been the Marana excitation.
Yeah. So not the fermion, not the real fermion. Okay. So in the sense that okay, this gapless lead to spin liquid, and you can apply a 1-1 field. You can gap out the spectrum, and which actually you can have different non-abelian ends.
So on the application side, that people could find the Marana fermion in spin liquid.
Okay, that's no.
No.
But you have to find spin liquid first.
Yeah, I have to find spin liquid first. But if I do have spin liquid,
okay. I'll run through the. Okay, so I'm skip the last example. This. I still want to talk about it. So okay. I quickly talk about this. So basically, this is so-called quantum nice. So if you have a particle lattice, you can have you can study SX3 model on a particle lattice. So basically, this is the Ising term, and these are like quantum fluctuations. This Hamiltonian has a U1 symmetries. So basically, the conservation of the SD. So let's take the classical limit. So this term is much larger. I can write this Hamiltonian in terms of sum over the Ising spins on this tetrahedron and square. Okay. And so this actually to minimize this classical Hamiltonian, we basically just say, okay, I want the sum of this tetrahedron to be 0. And if you have Ising spins, they actually have only 6 configurations, right? So I can define this in out, and the sum of this to be 0, I have only 6 configurations. So if I extend this to the parachord, I get this number of configurations. So this coming from, if I put all the, say, up tetrahedron with this one of the 6 configurations, and they are connected by this down tetrahedron. So without this constraint, my down tetrahedron has 2 to 4, 16 configurations. But there's only 6 allowed, so I have a reduction. So this is the kind of a configuration I have. And this is extensive. So I have a residual entropy of this much for the classical system. And so this is called a classical spin ice. And the reason why it's called classical spin ice is because it's a magnetic equivalent of the water ice. And this entropy actually can be measured, and people actually studied it and found that very agreement with some classical one. So when you turn on quantum mechanics, you allow this, although also in this region, you'll find that lowest order the effective Hamiltonian with this so-called ring exchange term. So basically, you have this operator. What it does is to flip all the spins on these hexagons. This is the ring exchange term. And it turns out it's very this can be effectively written in terms of some like emergent quantum electrodynamics. So one can introduce 2 fields. Basically, you have a field along the bonds of this pure diamond lattice, and also have there's sort of like a gauge field like that. Right? So these are fields living on the bond. Okay, so at the end, because of I also have this ice rule, and this ice rule becomes a lattice Gauss law on each for this B fields. So the low energy effective model is like this, and so this is it's a U1 gauge symmetry, but this A field can only define up to 2 pi because it's on a lattice or because of this cosine term. So this is a compact QED, what people study in lattice gauge theory. But it's slightly different because we have a spin 1/2. So this BR has a plus or minus. It's not 0, 1, or like vacuum state. So this introduces some kind of fluctuation. And the interesting thing is that in 3D, this theory has a deconfined phase, so-called Coulomb phase, which means that the string tension, the interaction between these two these excitations, test particles, are actually one as well. So the effective theory becomes a non-compact QED, so it's an emergent photon. So this is kind of the schematic picture of kind of excitations you have. So you have a ground state, and they have emergent photon excitations, and there's a in our language is McCulloch monopoles, which is leaving on the plaqué of the hexagon of the paracord, and you also have some electric charge, which is a much higher energy. So, so it is so what type of quantum speed liquids? We're going to cover some simple examples, and there's a lot of things, especially this Dirac spin liquids. Another thing that people are interested in. This can be supposedly stable in two dimensions. When I talk about this pure gauge theory is only stable, you have a deconfined phase only in 3D. Okay. How much time I'm over time?
5 minutes?
5 minutes.
Okay, so so where to look? Frustration. Well, this is my favorite systems. So what I'm going to talk about in the following is this carbonate system, and it's actually carbonate. That's Japanese for this basket. Okay. So what's frustration? Frustration basically is you think about in an IC spin, you got a triangle, you spin up, you try to put the spin up, spin down, try to make all the bonds happy, and you realize you cannot do it because they want to form anti-parallel. Okay. So the only way you can do is make them equally unhappy. So for this configuration, you have two degenerate classical configurations. And you can think about you put it on a large lattice, then you get a lot of classical degeneracies. So you have a degenerate manifold, you turn on quantum fluctuation, anything can happen. And experimentally, how do I look for the frustration? In the mechanics system, one energy scale is so-called Curie-Weiss temperature. So normally this corresponds to kind of mean field kind of ordering temperature. And in the frustration system, instead of going to long range order, you're going to a region of this cooperative parameter. So sometimes the system freezes, sometimes it doesn't. And so this ratio is actually the measure of degrees of freedom, degrees of frustration. But this is also a very arbitrary definition. So there are some material candidates, some organic systems on triangular lattice, some cadmium is a Herbert Smith side, and there are 3D systems. And this, I think the well study one is cesium copper chloride. It turns out it's described by 1D physics. Yeah, so these are the lattice structures. And it turns out, so this will give you this Kita's kind of physics, Kita's model physics, and this should be the Kagome-Heisenberg model, and this is a triangular lattice on the organic compounds. So what tools do people use? People use neutron scattering. So this is the electric neutron scattering to look for the excitations, and they see it come to be a spin-on continuum. This is another compound people use NMR, and this is sort of I think this is a famous experiment by Matsuda Sensei. But basically, you can measure the thermal transport. So when you apply a field in this compound, there's a signature of this quantization from somewhere. It turns out this Herbert Smith, I know this Kagome compound is pretty dirty, and it's amazing that the NMR people can separate different kinds of spins, and they identify some random singlet states. Okay, so this order again plays the important role here. So I'm a theorist, so you think, okay, maybe let's try to solve the Heisenberg model on this simple lattice. And what is the ground state? We think this is kind of trivial, right? This Heisenberg model on this. It turns out people have been trying to solve it, including some people in the audience. Okay, since 1994, and as of I think last year, there's still paper discussing this. So this is I think this is from Ian's paper. They compute the gap, the gap, and they found that there's a gap spin input. But it turns out these people often argue that okay, you're not crossing the right Dirac point. So basically, you insert a flux because your finite size system to cross the Dirac point. They claim this is a gapless Dirac spin liquid. Also, it's confirmed by an infinite tensor network kind of study, which will be a gapless spin liquid. But we try to do it, and by adding some term, and it seems to be stable. But what's the effective theory for this actually is not clear because there's no symmetric protection for Dirac spin liquid. But why introduce perturbation? Why is this spin liquid stable? It's all the question. Okay, sorry, I have to rush through my slides. So there's a lot of progress on theoretical understanding of quantum spin liquids, especially the progress of numerics. A lot of cutting edge technology applying to these frustrated models. And one thing we didn't talk about is this classification schemes by a la Xiaofang Wen, like hundreds of different types of spin liquids. And I hope I convinced that entanglement play an important role of understanding these spaces. And we need more experiments and theory studies. What's been missing, okay, so we didn't talk about partial construction, possible variational wave functions. We didn't have a chance to talk about adjustment free group, right? No discussion of partial spin liquids. And also, we didn't have a chance to discuss here things. We're interested that these are some not so recent references. But it's always interesting. Okay, thank you.
Thanks for an interesting talk. I have one remark and one question. So remarks addressing the first things question regarding the topological order space. So I talked to Shinaoka many years ago in Hualien. He mentioned that there is a misuse or abuse of the term topological. There are two kinds of topological states. One is protected by the symmetry. That is what we usually call topological materials. That was, becoming really a hot topic early 20s, right? Early 2000s. But there is another type of topological state, which is exactly spin liquid, which is not protected by the symmetry. And one example is a quantum Hall state. There's no symmetry protected this edge moment, and yet it is a topological order space. So the spin liquids belongs to the classification of the topological order, which is not protected by the symmetry.
So, so in the modern language, it's the topology insulator are actually symmetry protected topological order. And what I'm talking about is the symmetry enriched topological order. So,
yeah. So
it's a short range entanglement.
That's right. So in Shinaoka's term, we should not call topological insulator a topological phasor method, because it is only protected by the symmetry. If the symmetry is gone, this phase is gone. All right. Okay. And the question is the real material which could be called liquid candidates. So is there a really a confirmed material that everybody agrees is a liquid material? No. This is exactly the the issue here. So there's always some controversy. So for example, rosmicide and say even the KTAF, even arpagocinium, whether this is really realization of a KTAF liquid is an issue.
So there's an extra term in this material, and
right.
Also, I mean, zero field is a stripe order. But when people predict that if you turn on magnetic field, it might be a spin liquid state, but I'm not sure.
So there is only signatures, but it's not really smoking gun.
Well, in Fuzzy 1D, there are very clear pictures. So you mean cesium chloride, cesium copper chloride, and a lot of this Fuzzy 1D, they can really see this spin-on continuum, and but that's again is related to the 1D physics, not so much about higher dimension. But another thing is. Actually, people realize historical quantum computer or local computer are very useful yet, but I think they will try to grade it, and they see this topological order state on a quantum computer.
Well, it's non-abelian stuff as well.
Yeah, but also there are always some people, right? They both, I mean, the Poland and also this. So, yeah, so I agree with you that material is probably people still looking, the people are actively looking, and in the past decades, a lot of times people realize there's a lot of things going on, and your interpretation have to change. But that's why we need more experiments and more material. And I think Kita material is one of the first that people take a model and then try to design, so try to look for materials. And also like purpose inside, in a sense also.
Thank you.
About the implement that computer laws that
gamma term. Am I right that the gamma term because it overestimate entanglement on the surface term because of the
Yes.
So there's some constraint of state.
Oh, this argument. Okay, so if I have independent crossings, then I basically I don't have a loop, right? So they're independent basically. So it's proportional to the number of crossings here. But it belongs to a loop. So for example, let's look at this one. So this is basically the same object, right? So you have two crossings, so I'm gonna count.
So only citation that will give the string name. Contribute to the gamma. I don't know for citation.
No. So basically, you cannot count this the same excitation. You count this as the same excitation. So that's why you divide by. This would belong to the same group. In this picture, right? So you have so all these loops, I only consider close loop versus the crossing. So all these crossings, I always cross twice. Unless I have a single open loop, I don't cross it.
Until gamma and even I don't know about it talking about right care like excitation.
That's the question. Yes, I know that's coming from field theory, the counting of the patient. How does it relate to here? Why is there? I think that the loop picture, you clearly see there's a correction with this axis, but I can answer why the expectation, the content of this gamma, and also why this minus one becomes more complicated case.
I think some information might hope is that if that's the ground state, the lowest the excitation will be you try to break some of the loops. So that would be
So we subtract some degree of reason.
Not really subtract. I mean, it's more like if you have that particular ground state, you actually bring down the possible excitation. Which then you constrain the possible excitation.
So also I remove it.
Not remove it, so you have to constrain.
I mean, the ground state is a lot of loop, and that configuration also restrict the excitation should be broken of some of the loops.
So for example, if your excitation is now open loop, right? Yeah. So you don't have this constraint, then you don't have this gamma.
Yes.
Because so now because you have this constraint, so now you have to it's more constraint, so you have to subtract them. How much?
So basically, the ground state is kind of loops, so it's constrained. But somehow this gives you the information of how when you open the loops, what kind of excitation you have in here, but now the minus.
Yeah, I have a question. So is there an easy way to understand the excitation like this string? I never understood that now. I think of it, it's a long way then, but one of the no one.
If you know, tell me.
Probably the
you can write it.
One in the but actually there are a lot of gatlets in the yeah.
Yeah, because we have some other study in mind, maybe like a potential they will answer also something similar to that. But I guess it's
very hard.
One quick question. Think the entanglement entropy is proportional to the area of the boundary. Is it somehow related to the entropy of black hole?
Yes.
Yes, that's actually that's very accurate.
So it's a very accurate.
Yeah, so in like string, now whenever they study black holes, like area and like entropy kind
It's actually directly related.
Yeah, it's all they can do nowadays.
Okay, due to time, maybe we close this talk. Thanks to our speaker again. Please stay in 1 minute. For 1 minute, let's take a group picture.
Very important.
And
今天猜对了一件事。
现在做这个教育，然后
但是因为黑洞真的特别，因为它的那个 entropy 跟设备
也不对，或者说你要怎么描述？对，
所以说
你要有它内部不同都不一定要进入
这样的
中间。
当然做不到，只能照到中间。对啊，
这边过来，这边过来，这样子才属于镜片。
放 break， 然后往中间一个 part 跟另外一个 part 一个 break， 比较就是 part。
东南北。
刚刚的影片是里面带影片是里面快的。
是白牙麦克风
都有，然后你说他那个 behavior， 他们都
在这件事情，在研究这个命理轨之前，他们
那边后面的进来。
And the section is split. And the second thing. I think the talk will be starting in about 5 minutes. We can do that a little bit.
Hello, do you hear, sorry, do you see my pointer?
Yes, I can see your pointer.
Yeah, okay, thank you.
But you need to move your pointer, otherwise it will be hidden. But like the maybe.
So.
Yeah.
I cannot write anything on this, but maybe better to have a bigger screen.
So do you want to check the person to this?
Sorry, I cannot hear your voice very well.
Is it better now?
Yes.
So my question is, do you want to use the laser pointer style of your cursor, or you want to use the pointer? It's fine.
So you see my pointer, right?
Yeah, yeah, I can see that pointer. Yeah.
Yeah.
So you'll use that directly.
Yes. Yes.
Okay, no problem.
Yes, I can. In Keynote, I think there's no such thing. Keynote had.
Yeah.
Had or something.
I hope my pointer is visible.
Yeah, I think it is visible. OK， 好，谢谢。OK， 下面有5个 answer。
I'm thinking whether he can hear without expressions.
So you do hear Yanni asking questions.
Sorry?
You hear my voice?
No.
Okay. So it be, I guess. So if you want to ask a question, maybe one way is to talk to the front desk and speak directly to the microphone, or I will leave the microphone to you. Thanks. Then we will start on 2 o'clock sharp. Yes. I'll probably start the introduction a little bit first because this talk is an online talk. So if you have any questions, please go ahead and I'll bring the microphone to you. Hear what you're trying to ask. Okay. So also I think today is our great pleasure to have Professor Hiroshi Shinaoka coming from the Saitama University. Is a pioneer in the study of this SNL sample representation for some hidden low-rank structures. Essentially, he did a lot of important work on the study of the field theories, especially for strong correlated system. Also, is in a collaboration to develop international scope library to help people to compare and explore the related low-rank structure. So I think I'm not going to occupy much time. That will with the Hiroshi.
So thank you for introducing me and inviting me this nice workshop, but I'm feel very sorry that I cannot attend the workshop in person. But yeah, maybe we could please ask questions if you have any. And today I'm going to talk about using or exploiting some hidden Lorentz structures in quantum field theories by using tensor networks. And this study was supported by many grants and also collaborators from many university and institutes like TU or LMU Munich or and University of Freiburg and more. So, but I don't have time to introduce all of my collaborators, so I just show names in each page. So let me start my talk. So I'm going to talk about many things, but essentially 3 things. So what are quantics or quantized tensor terrain and tensor cross interpolation, TCI, and how we can use them for quantum field calculations. And finally, the new TCI algorithm and open source libraries, C++, Python, and Julia. So they're what I'm going to talk about today. So my original motivation to jump in this field is actually ab initio calculations. I've been working on material calculation using dynamical mean-field theory and similar methods. There are many diagrammatic theories to compute electronic and magnetic properties of strongly correlated materials, like Migdal-Schberg theory for superconducting states, or GW, and functional RG for magnetic stuff. But we end up with solving huge diagrammatic equations, including correlation function or Feynman diagrams, Green's function in high-dimensional space-time domain. So sometimes, and in many cases, it's become too expensive. So even you have nice theories, so you cannot apply your theories to nice materials. So that's one technical bottleneck in our field. So that's why we have been working on developing dimensionality reduction technologies for quantum field theories. So let me show some example, some numbers. So if you do mean-field calculations, you're still fine. You only consider effective potentials coming from other electrons. But in non-equilibrium case, it depends on two spacetimes, here and here, incoming electron and outgoing electron, right? So it becomes already expensive because usually your system has coexisting different scales, length scales or energy scales, like large bandwidth and small low temperature physics of interest. So you need a dense grid, two-dimensional or for two space-time points. And if you do or want to do more novel theories, like non-local extension of the MFT, so you have to deal with effective interactions. And you have two incoming electrons and two outgoing electrons. So this object depends on 4 space-time points. And if you have different length scales, you need a dense grid for each grid axis. So you end up with huge memory. So you are essentially dead. So that's why we need compact representation. And compression is not enough. You want to do computation in compressed form. That makes the story a little bit more difficult. So recently, in a field, there is many great progress, especially for imaginary time or maximum frequency space. So this space is somehow special because any Green's function, imaginary time Green's function, is connected to a spectral function in real frequency through a Riemann representation. And this kernel is known as an analytic continuation kernel. And this is the condition. So I'm not going into details, but the point is Green's function, imaginary time Green's function has less information than the spectral function. So we can make use of this prior knowledge and by decomposing the kernel, so we can get a compact representation, right? Intermediate representation, invented me and my collaborators, and some similar method from Crescent's group, and some extension of IRL from CCQ. And these technologies are great because we can reduce the memory. Sorry, there's a mistake. For any time correlation function from beta to the n square to this small weak scaling. Still, memory footprint diverges at low temperature, but the reduction is huge. So now you can even use these technologies in an open source package for electron phonon interaction computation. So, but unfortunately, this kind of technology cannot be generalized to other domains, like real-time, real frequency, or real momentum space. So we need more general approaches. So what we need. So now tensor network gateway. So tensor networks or MPS has been, DMRG have been, were invented to describe the ground state properties of low-dimensional quantum systems, like what the Hubbard chain. But recently, people are trying to use this dimensionality reduction technologies for many targets beyond the conventional target, right? Image compression or machine learning or solving some classical or quantum field theories. So we are going to talk about many quantum field theories. Okay. So in the rest of, Okay. So in the rest of my talk, so I'm going to introduce two important concepts first, QTT and TCI. And then I'm going to introduce our recent work on quantum field series and new algorithm. Okay, there is no freelance. There is no single efficient algorithm for everything. So you have to use some hidden structures in your systems. And if your system has some symmetries, or like periodicity or some symmetries, you have to use some group theory. And in quantic representation, we make use of separation of different length scales in your system. So such a separation of length scale actually are hidden in many systems, like in turbulence flows or quantum field theories and in other systems. So it's more general concept than the analytic continuation kernel. That's why I started to use this tensor network. Okay, but before going to detail, let me start with some this slide showing tensor network diagram notation, because I'm not sure most of you are familiar with this notation. So scalar is a dot or square without a leg, and vector is a square or a circle with a single leg sticking out. And matrices, matrix has two legs, and three-way tensor has three legs. So if you connect two object through with some shared indices, this means you have to take summation over the shared indices, like Einstein notation. So in this case, this object denotes matrix vector multiplication. Well, this should be A times X. and the opposite direction is decomposition. So if you have three-way tensor or R-way tensor, so you can decompose this guy as a product of smaller matrices or tensors. And these are red bonds are called virtual bonds because they are not physical. They are introduced to carry information or entanglement between different indices. And the size of these indices are sometimes called bond dimensions of this matrix product state or tensor terrain. So this is what you need to for understanding my talk, I guess. Okay. So now I'm first going to introduce what are quantic representation or QTT. This was invented, well, first introduced for image compression in 2005, but mathematically, our foundation was built by these guys around 2009. So the idea is quite simple. Let me consider a function depending on a single variable defined on this domain. So this function could have many features, small fine features or wide features, but you don't know where they are in advance. So what you could do is you put some uniform grid. In this case, the number of grid points is 2 to the power of R. R is the number, right? And so if you increase R, so your resolution becomes exponentially fine, and then you can resolve 5 features in f of x, but the numerical data size increases also exponentially. So this is not a good idea. If this function has some structures, simple structures. So in quantics, so instead of using our single index or integer, so we map this integer into a binary, to the binary format. So now our integer is represented as like this, and sigma 1 or sigma are there either 0 or 1. Sorry, it's not shown here. Or graphically, sigma 1 corresponds to the largest length scales in your system, and sigma r corresponds to the smallest length scale in your system. And they are different by several of magnitude. So there are these indices, well, describe the dependence of your function on exponentially different length scales. So, but we haven't done any approximation now, so far, by now, because your function is still numerical data, actually R-way tensor on in this representation. And then if there is some separation length scales, even you have many different length scales in your function, they are not strongly entangled. So we may be able to decouple this, decompose this large tensor into the product of small tensors, like tensor terrain. And if the bond dimension, bond dimension means the size of these virtual bonds is small, so we have a nice compression rate. So this is called quantic tensor terrain. And quantic tensor terrain can exploit separation length scale, and it's, well, completely different way of using entanglement in the system. Okay. So we can easily or in a straightforward way are extended to multivariate function, like an dimensional function. And the idea is we do binary coding for each variable, like this. And we apply tensor train approximation again for the discretized function. So there are many different ways of ordering these indices, but we usually in this talk use interleaved representation or fused representation. They are almost identical in the sense that binaries or bit indices for the same length scale are at the same, almost the same place like this. And these are for the same length scale. These are for the same length scale. And the interleaved representation, we put them side by side, separatedly, or in the fused representation, we combined these indices in a single big index. So it's just numerical convenience. Sorry. So the reason to put indices for the same length scale side by side is usually these indices are for a storing interval in a physical system, as I will show in my talk. So let me show some analytical example of compressible functions. And exponential function is the most simplest case. So exponential, this guy can be decomposed into the product of like this. So you can easily see that the bond in QTT, the bond dimension is 1, because this is just direct product of many small exponentials. And another interesting example is the identity matrix. So we put 0 except on the diagonal line, and this can be written like this, and by using Kronecker delta function. And this is horrible for SPT or eigen decomposition compression, because singular values do not decay. But in quantics, so you can easily see that this Kronecker delta is a product of Kronecker delta functions for each length scale. So again, if you put two indices for the same length scale in a single tensor core, so you get a tensor train of bond dimension 1. So this is a critical difference between the normal convention and quantics representation. So somehow QTT has much scale properties or resolution. So if you want to learn more, you can visit some website written by Miles, or you can buy applied math book on QTT. But it should be here. What is less compressible? And here is a simple example from our math paper. And now our function is 1 inside this circle and 0 outside this circle. So that means we have this continuity on a curved boundary here, right? So the angle changes gradually, right? And if we apply QTT naively to this function, so actually bond dimension increases exponentially with R. R is the number of bits. And this is because as we increase or make our resolution finer, so these independent patches or linearly independent patches this number increases exponentially. So we cannot compress these patches. So that's why the bond dimension increases exponentially. But this only happens if there is no broadening and the discontinuity is living on a curved boundary. So if you have some discontinuity on the line, it should be fine. QTT can compress it, but curved surface is not good for QTT. So, so I have introduced our QTT, so I move on our tensor cross interpolation. So the idea is, even you have a function or a tensor, or large tensor, you want to construct Laurent tensor train approximation for this guy. But if you apply SPD or a QR decomposition, so you have to read out all the tensor elements from this tensor, or you have to evaluate your function for all possible combination of indices and store the result in a memory and apply SPD. So that's really expensive, and the computational complexity scale exponentially with the number of legs. So, but if we know that this function has a Laurent structure, we can avoid it empirically. So, but before explaining TCI, maybe you can learn something from matrix version, MCI. So the standard approach to decompose or approximate a general matrix is SPD. But in MCI, we randomly or adaptively select important rows and columns. We sample our elements. Then we construct our MCI representation by correcting our selected rows like this, and columns and rows. And this pivot matrix consists of these points. So this formula consists of only sample points, no addition, no subtraction. And we can easily see that this interpolation, this formula matches the original matrix always on the selected columns and rows. So if we choose these pivots or columns and rows are in an adaptive way, or heuristically, so we have small interpolation error between selected columns and columns, rows and columns. And there are many heuristic algorithms to find good pivots. And to get some feeling how it works, so I'm going to show some toy algorithm. I'm not saying this is practical algorithm. It's just super naive algorithm. So let me start with bond dimension one. That means you do line search, but we do not read all the elements, and we find where the function takes the absolute maximum. So approximate, of course. And this can be done to some random line searches. If we find this point is approximate maximum, you construct bond dimension one a rank one approximation for this matrix. So now this is an approximation. Now then we try to find where the interpolation is still large by again random line search. But we do not visit all elements. We just do random search because we don't need the exact maximum. So if you find this is well, here's the interpolation error is still large, so you can add it to your MCI. You can construct round 2 approximation interpolation. Then you can continue this procedure until you do not find any, right, bad points. So this is different from our SPD because somehow this minimizes our interpolation error. Sorry, there's some misspell. In the absolute maximum, maximum norm error sense. So I'm not going to discuss in detail, but we can extend the MCI to tensor network or tensor train. And we end up with introducing many pivot matrices. And the bottom line is, so we can still sample the tensor or this function in a huge configuration space randomly and adaptively to find where the interpolation error is big and add sampling points or interpolation points adaptively. So the number of function evaluation or the number of every element to be read is scales like L times chi-squared. That means that is the number of elements in the tensor train resultant. So how we can use this technology for quantum field theory? This was pioneered by Uriel and other collaborators, essentially from Xavier Weinthau's group in Grenoble and NSYSU. And I'm not involved, but I spent 2 pages. So they try to replace quantum Monte Carlo sampling by TCI. But how? So in diagrammatic Monte Carlo, we expand some quantity of interest in terms of Coulomb interaction, U. So what you have to do is you have to determine this guy, coefficient, Taylor coefficient, right? Expansion coefficient. But it's super difficult because usually this scalar is obtained by integrating some high-dimensional function in high-dimensional spacetime. And usually we do use our diagrammatic Monte Carlo to do that, but it suffers from sign problem or sign cancellation. So what they did is, okay, let us construct first tensor train approximation or TCI interpolation for this guy by sampling this function in the huge configuration space. Then we get this kind of decoupled representation. Once you get it, so integration over all variables can be done locally because we can integrate this guy for U1, integrate this guy for U2 first, and we do tensor contraction afterward. So the question is, of course, our function is Laurent. And they applied their idea to a single orbital Anderson impurity model in real-time formalism. And this is, their TCI approximation. And this is our average sign in Monte Carlo sense. And I think epsilon D is a control parameter to break half-free, a particle hole symmetry. So you can see that our average size is super small in this region, but our factorization error by TCI is not affected by a sign problem. And the interpolation error or error in the resultant quantity decreases algebraically, but much faster than Monte Carlo, right? Monte Carlo will follow this line, but TCI follow this line. It's faster. So there is no free lunch. So this algorithm depends on Lorentz structure hidden in Feynman diagrams, but this is an alternative or complementary approaches to Monte Carlo sampling if your function has a Lorentz structure. But at this point, they didn't use quantics. So later, we decided to join forces. So you see many familiar names here. Okay. Now in this section, we briefly discuss three things. So I'm going to focus on quantics, and I want to show you how compressible and I want to show you that actually correlation function, Feynman diagrams, space-time dependence is compressible in quantics. And second, actually we can solve many diagrammatic equations in quantics representation in compressed form. So we can do convolution and FFT and many things in compressed form. And third, by combining QTT and TCI, we can do efficient integration, even for multi-orbital cases. So let me start with the first one. So in our paper, so we applied SVD. So at that time, we are not aware of TCI. So we had to use SVD. So we use a rock station with a huge memory. And we apply SVD to many numerical data we got from our collaborators, like spectral function for Anderson impurity problem, or single orbital, Harvard model Green's function, momentum space, computed by some diagrammatic approximation, Flex approximation, or three-frequency vortex function of exact solvable models, or real-time Green's function obtained by Numerical DMFT, and multi-orbital susceptibility obtained by DFT plus DMFT. So we found empirically that the space-time dependence of correlation function are actually compressible. So let me show you some example. And I want to show you some intuitive understanding why quantics is good. So here is an example from Philip Reynolds group, and this is a real-time Green's function computed by non-equilibrium DMFT, and the system is probably antiferromagnetic mode phase excited by some pulse, and so you see some relaxation process along the diagonal line corresponding to the equal time component. And the retarded Green function is completely zero in this triangle by definition. So, and as you can see that we have many oscillations and exponential decay and even discontinuity here, right? But quantic expectation does not suffer from these features. structures. So you can see that easily get 3-digit accuracy, and the compression ratio for the data size reaches 1,000. So the number is just a number. The point is, quantics is very good at representing diagonal structures or line discontinuity. This is because, well, you remember that I show you that the identity matrix is compressible due to merge scale nature of QTT. And that's intuitively explain why QTT doesn't suffer from this line discontinuity on the diagonal line. So there's another example is multipolar susceptibility of computed by DFT plus DMFT, or it's already published last month. And we computed some multi-orbital local susceptibility depending on two fermionic frequencies, nu and nu prime, and depending on spin orbitals. And because we have 6 local states, and this is 2 particle quantity, so each index I and j is the size is 36 and 36. So the advantage of tensor terrain or QTT is we can encode spin orbital dependence in the same tensor terrain. Yeah. So we can then combine our quantics representation for frequencies and spin orbitals. So here is bond dimension. So along the chain. So you can see that the bond dimension is much smaller than the worst case without compression. And here is some reconstructed data for some spin orbital component in 2-dimensional frequency space. So you can see that we have a sharp feature on the diagonal and broad features, and QTT can describe this feature in a compact way at the same time. So in our field, in DFT plus DMFT field, people have been trying to construct a good basis to represent this diagonal line and broad features at the same time, but QTT naturally can describe these features. And still, we have been working on how compressible space-time dependence of our imaginary time propagators. So we recently did some numerical experiments for random pole models. We put random poles and correlations are random, and we push this model to very low temperature to see how the bond dimension grows at low temperature for very complicated systems. So we found that actually for much frequency case, even the bond dimension stops growing at low temperature, even for metallic case. And this is kind of surprising in our field because even the best conventional representation for imaginary time or imaginary frequency space, IR, invented us or DLR from CCQ, the data size increases, continues to increase at low temperature. So this is, in this sense, this is surprising, and this means QTT may outperform the known best representation, even for imaginary time propagators. So now we show that many space-time dependence on many correlation functions are compressible. But of course, I didn't describe the detail, but I hope you are almost convinced that and they're compressible. Now, the question is how to solve equation. So to solve equations, like Dyson equation or Bethe-Sapet equation or, so you have to do several basic operations. One is Fourier transform between momentum space and real space, or time and frequency. In quantum representation, this operation is transformation is trivial because this linear transform is represented by a matrix product operator with a small bond dimension. In practice, it's something like 20 or 10. And the trick is before and after the transform, we use binary coding for our K and R, but we reverse the order of the indices, right? Here we have RR and we have K1 here. So, but after the Fourier transform, they correspond to the same length scale, right? So the small bond dimension MP, this MPO, indicates that Fourier transform is almost independent, can be performed independently at each length scale. That's why we have a small bond dimension along different length scales. And this has been known in quantum field theory field for many years. And recently, people in conventional physics realized this can be exploited to do efficient computation on a classical computer because the bond dimension is super small. So if your function is compressible, even you apply your QFT MPO, so the resultant MPS or tensor train should have a small bond dimension. And this can be done very efficiently. Okay, so another important operation is matrix multiplication. So if you have two objects, like, and this could be just some Feynman diagrams. And your function depends on T and T prime, and T prime and T double prime. So once you have a QTT representation for these two guys, so computing C is just, performing this tensor network construction or like this, and do recompression. So if A and B and C have the same bond dimension chi, the computation time scale like this. So the power is big, but still okay. So essentially, these QFT and convolution matrix multiplication are enough to implement many diagrammatic equations. So let me show you some example from our collaboration with Werner's group, published this year. So what we did is we constructed our QTT representation of non-equilibrium Green's function on the Keldysh contour. So we have our imaginary time branch here, and we have two branches for real time. And as we have shown in the first paper, Green's function defined on this contour actually compressible. And these arrows indicate some trivial symmetries between different components. But, because our Green's function is compressible, we can implement two things. One is, so non-equilibrium Dyson equation looks like this defined on the Keldysh contour. So each multiplication It's just matrix multiplication, what I just explained. So first you can multiply sigma and g if sigma is known. And you can multiply this guy with G0 and add two tensor trains to get new G. So you can easily implement iterative solver of Dyson equation. So computing sigma is a different business. But if you use second order cell phone energy, which is popular choice for in equivalent DMFT, so what you have to do is, again, convolution and Fourier transform, which can be done in Q quantics. So now we have QTT, pure QTT implementation for non-equivalent DMFT, and we are now working on more efficient implementation in collaboration with Werner's group. Okay. Now the third is integration. So integration is, before going to physical result, I will show some toy example. So this analytic function, I do not show analytic form because this that looks ugly, but has features at different length scales. This is order one, largest length scale or smallest length scale right here, right? This is very small. And if you want to do integration, you could apply Legendre, Gauss-Legendre quadrature, but it's not possible because you cannot even store the numerical data. But in quantics and TCI, so you can learn the function as a tensor train on the fly without storing all the numerical data, and you can get compressed tensor train object. So once you get it, you can do anything like Fourier transform and integration like this. In this case, to reach its significance, we need only 1.5 megabyte. Of course, this is, well, toy model. So now we're going to show some physical example. And first we try this idea, quantics plus TCI, to our Brilliant zone integration. So here's a simple example taken from this paper. And we consider a Hardin model, just single, non-interacting tight line model, and compute Green's function in the momentum space. And here we have a big signal or sharp peaks. And instead of solving Dyson equation on every grid point, you can apply QTCI. That means each time TCI requires read some elements, so you solve the Dyson equation on the given K point, and you feedback this result to TCI algorithm. So then we can run the momentum dependence without storing the whole numerical data. And this is interpolation error. So it's super small, right? So the advantage over SVD of the numerical data is, of course, it's much faster because as you increase the number of bits, so the number of grid points increases exponentially. So after R equal 10, so SVD is already too expensive. But TCI, so we randomly and adaptively sample the Brilliant zone. So essentially, computational time scale only linearly without the number of bits. And it's still, I don't know, I'm not sure why, but our numerical experiments indicate that bond dimension of our QTT representation for Brillouin zone momentum dependence increases scale like this at low temperature. And this means, of course, the bond dimension diverges at 0 temperature. And this is somehow expected because I already showed that the example of a circle, right? The bond dimension grows exponentially with R. And at exactly low temperature, and this Green's function is computed at the lowest Maxwell frequency, we have no broadening, thermal broadening. So QTT bond dimension then diverge if we do not do some change of variables. So now we are trying to use this QTCI technologies for more complicated multi-orbital self-analysis. So this was by one of my students and in collaboration with Hoshino group in Saitama. So what we chose is 3 orbitals plus phonon models, local phonons. And we have 12 flavors and 3 from orbitals. And we have 2 spins and we have 2 number modes for superconducting states. So we now evaluate second order self-energies looking like this. So it looks nice, but this function is living in a high-dimensional space because ether corresponds to phonon modes, and the size is 6. So we have 6 phonon modes. So we now have 6 times 6 times 6. And we have 3 time variables. And we have spin orbitals. And this is 6, 12 times 12. So we have to integrate this function over all internal variables. And that's not easy. This is not easy because if you look at the function on a thumb cut, so you can see that function has a lot of line discontinuity, this lines of discontinuity, and the structure near the discontinuity become finer and finer at low temperature. So we have similar structure for phonons. So the question is if we have a still low-rank structure for tensor train in quantics, and if more importantly, so we can learn DCI by adaptive sampling in this high-dimensional space. And this is our result. And alpha is an external field to break the symmetry and temperature control superconducting transition. Low temperature, we have superconducting or symmetry breaking. Yeah, like this. So this shows how the bond dimension varies on the chain. So you can see that bond dimension is small, and you can easily reach fine scales here in time. And this plot show how the interpolation error converges with increasing bond dimension for different parameters. And you can see that the bond error converges exponentially with increasing bond dimension. So I don't have strong opinion on this point, but it's quite interesting because in the previous paper, pioneer paper by Uriel, they show parallel convergence without quantics. So we are solving different models. And so we shouldn't do a direct comparison, but still this exponential convergence is promising to me. So recently we pushed the calculation to larger bond dimension, well, requested by referees. So now you can see that your query, at least for this blue line, the exponential line convergence can be seen more clearly. So we still some wrinkles here. So now we have a brief overview how we can use quantics and TCI for quantum field theory. So, but in the last section, I want to show you some new TCI algorithm and open source libraries. And this was recently uploaded to arXiv. And I want to this manuscript contains three things. One is robust and stable TCI algorithm, and open source implementations, and self-contained introduction to quantics and TCI. So if you are interested in these technologies, you may start with reading this manuscript. So I haven't explained well the details of TCI algorithm, but you can see that in the toy algorithm we add only one pivot at once, right? In the full metric version. And this is the same for TCI as a conventional algorithm. And we always add new pivots and never remove redundant pivots. And this is numerical, sometimes unstable, but in the new algorithm, so we use a new algorithm to add order chi many pivots in a single local update, and even remove redundant pivots at once. So we call reset mode, and which is more numerically stable. And now this mode is default. And the other thing is, in addition to local update like DMRG for finding pivots, we can use extra information on the linear function. If you know the symmetry of your function, you can exploit and this information and add manually new pivot into a TCI object. Or in our preprint, actually we combine local TCI algorithm and global random search. So this was, well, critical to stabilize the TCI, QTCI for multi-orbital cases. So, but I don't have much time to, so if you're interested in using our libraries, please visit our website, Tensor4All, where you can find our link to literature papers and links to our repository. So the libraries consist of two independent libraries. One is XFAC for C++ and Python, and Julia, mainly developed by Merck and in Munich, and myself. So, and the Julia libraries consist of many libraries like for TCI and quantics and QTCI and some interface with ITSS. So let me show you some example. And if you visit our website, so you can find tutorial pages for C++ and Python. And you can learn how to use them, use the library, XFAC. For Julia, so it's a bit old. We have now more examples. And you can see that many examples, and you can run, as a Jupyter notebook. So here is one example. how the Julia code looks like. So what you have to do is you define your function to be interpreted in quantics. You pass a function to quantics cross interpret of function. Then you get the interpolation easily. And here is a comparison between the original function and the interpolated one, and crosses shows the interpolation points. So we have also an example of quantum Fourier transform, and you can create MPO for quantum Fourier transform by like this, and we can perform QFT by contracting your QTT of your function and QFT MPO like this. So you can convert this object in MPO object and MPS object into iTensor MPS and MPO object and do contraction using iTensors if you like. So, and this algorithm is good for testing. Well, for go or no-go test, because TCI or quantics works only if your function has a low-rank structure, and you can apply a library to see how the bond dimension, how large the bond dimension is, and if yes, maybe you can think about how to exploit. And if no, you can try different representation, or don't try. You do not go further. So now let me summarize my talk. So I think QTT and TCI are good general framework for dimensionality reduction, especially quantum field theories, but the applications should be more general. And we are especially interested in ab initio calculations. And there are many interesting topics, for example, other than ab initio calculation, like extension to tree tensor networks, or structure optimization, or HPC, and so on. And so we have one open post position for this kind of project. And if you are interested, just let me know. Thank you.
Nice introduction. Are there any questions from the audience? Yeah, yes, please.
So can you hear me?
Yes, I can hear.
Okay, so the question is about this MPO for Fourier transform. Is that or is this Tensor question?
Sorry, I can't hear very well. So could you switch to another mic or?
Is it better is it better? Hello?
Sorry. Yeah, I can hear you now.
Okay, good. So now my question is that about the MPO for the Fourier transform. So
yes.
Is it already use some truncation or is exact representation? And what is roughly what is the bond dimension?
Sorry, your voice is breaking up. So could you speak slowly?
Yeah, sure. So the first question is that the MPO for the Fourier transform.
Mm-hmm.
When you construct it, do you introduce any truncation?
Oh, yes.
Okay.
Yeah, we usually introduce truncation.
I see. So
otherwise, bond dimension will be 10 times more.
Oh, 10, roughly 10?
Yeah.
I see.
But the result on tensor terrain is usually very compressible.
Mm-hmm. And
So after, yeah.
Yeah, please go ahead.
So yeah, but the point is, because the bond dimension of this guy is bounded by the factor of 10. But this bond dimension usually can be reduced drastically. Yeah, greatly by compression. Yeah.
Okay, thank you.
Please.
Hi. So you did this QTT on both the real-time Green's function and imaginary Green's function. I wonder if you can comment like because we know that the behavior of these Green's functions are very different. So is there some hint that on the complex plane, which works better? I mean, it's a general question.
Well, we have several different views of point. If we consider only compression, the data size, emergent time object has a smaller bond dimension than real-time Green's function, because emergent time dependence is more smooth and little information than real-time counterpart, and describing real-time dependence requires a more bond dimension in general. So this makes emergent time formalism a good target for QTT, but the point is, if we want to do Monte Carlo sampling or integration, we cannot use QMC for real time. So that means even if our bond dimension are larger for real time, QTT maybe, or QTT plus TCI will be have a big advantage for real time object computation. Does it make sense?
Yeah, thanks. So, are there any other questions from the audience? If not, I think we can thank Hiroshi again, and thanks for the really nice talk at QTT.
Thank you.
I think now we can enter the coffee break and some brief discussion. And the next talk will start at 3:45. Please come back on time. Okay, see you. I think a lot of like the questions are in your talk, so we have just so I think we'll close the Zoom channel and hope to see you in person.
Sorry, I cannot hear.
Hiroshi, sorry, I think we are about to close the Zoom. And thank you very much for the nice introduction.
Yeah, thank you for inviting me.
Hopefully we will invite you in person. You know, it depends on your schedule, of course. Now it seems like a little bit hectic. Yeah, thanks a lot, and looking forward to meet you again shortly. Yeah. Okay.
Thank you.
Thank you, and see you. Bye bye.
Thanks for the information. And you do not know me. No,今天都得申请。
Yeah.
这边有刘宗翰吗？姚友辉，姚友辉，反正我也好像有你资料的。那你可以给我。对，然后你要有那个这样。上面去吗？ 可以啊，你就帮我全部做脚底，我要看 reverse， 要再看一下。哦。电话号码。有实体，有些应该说实体高中现场讲要跟现场讲，不然Hello everyone, if you need hotel accommodation and the transportation reimbursement, and if you have the original for the hard copy receipt, you can hand me directly in person, or you can just email me via my email here. Okay? Sign what? 对呀，知道，拍到这样。还是那么。不能分析。
对啊，我觉得应该是你按，等一下会有部分，直接你有电视性。So, hi everyone. I think we will start with today's tutorial session. So, today the tutorial will contain two parts. The first part is the numerical tutorial given by Johnny, and the second part will be tutorial
And so the big idea of quantum tensor trend is that I have a smart way to, not linearize, not just discretize this endpoint, but instead, it's a smart way to do this interpretation so that you can make your resolution exponentially good with your result. How does that happen? Now, we're going to explain the key concept. So the key concept, to me, is really just to understand the binary numbers. Think of integers. We know that every integer you can use binary number or binary number. So for example, if we care about the function only on those points of integer point, right? If I care about the function will only do this one. Find some number. And you know each of these numbers that you represent by the binary numbers, for example, you have two binary numbers. You have 0, 0, give you 0, 1, 1, 1, 0, give you 2, 1, 1, give you 4. That's 3. Okay? And so you can keep going, right? So if you have more and more binary numbers, can represent up to 100 other integer numbers. And if you think about how many integer numbers then it's actually proportional to the edge, right? The number of integer numbers you can represent will grow exponentially with the binary number you have. You have two binary numbers, and you can represent 4. And 3 you can represent 8. And 4 you can represent 4. And so you can see if you have n binary numbers, allows you to represent literally this is kind of, to me, it's kind of the easiest way to understand. And so let's assume that, okay, now we're interested in the function. And you want to represent many, many numbers. Now, instead of writing the function, the 6 now containing this, you can now write the function because now your integer is represented by the function of binary. Right, so now your function is no longer a function of x, but instead a function of b1, b3, with bn, bi is with binary either 0. And if you accept this is true, then you might quickly realize that, okay, now this object is nothing but by definition, the tensor, again, we use this notation, have tensor with, let's say, 5x, you're given these integer numbers, you give it the integer numbers either 0 or 1, then you get right? So this is precisely like n-dimensional tensor. This is kind of the starting, the key concept. So now you can kind of convince yourself now find tensor with n indexes, they represent the function of value from 0 to 2 to the n minus 1. Okay, we have exponentially many three-point function of number. And of course, this is a huge object. This is just an original function, not useful at all. But if you can somehow contrast the tensors which were completely is the only path, then it's much cheaper. Right? And somehow this function, if you are interested, can be very good approximated by a lower ABS. Then you got a lot of and this is something you can deal with. This is kind of something okay to actually works. And you might wonder that, okay, I don't only want the integers, I want the real. Then it's pretty trivial that you can scale your, you can type arbitrary constant, scale your range, and you can easily compute and so on. If we can do this, then you can do it to arbitrary. Any A and B, and you simply put the data on the essentially the same. This, and yeah, it's all different for this. It is again, you got this in MPS, which not in this case does not represent by space, but instead it represents this quantized. You don't need to know any probabilities to learn about this. But so you have an MPS, and also you have some operator. Which can apply on the continuous one. Real operators. And you can apply this operator too. And I'm not going to show you how to construct this operator, but you can believe me that we can also present this operator using similar representation way, and we can very efficiently represent this operator. NTHU. This is also very important. See that I can put some right? And as long as you have this yes and you have this no, then all the things that are going to be learned does not care about whether you can apply all these arguments. The wrong state of this kind of continuous argument. And the times so yeah, so then you can apply all the Tensor techniques. And this is not easier to understand than Tensor content. We can play around and use this as an example for the application of our okay. Oh, by the way, let me make an announcement because I expect I have not used one so, but we have another tutorial. So we kind of expect that this tutorial will be a little bit longer, and we tend to start this like this. Yeah. So I can give you one example of how to exactly construct the function. I give you most simple function is just x. Okay. So let's say I want to write this function, x function, and in the binary representation, this x can be decomposed to the addition of 1/2 and 1/2, and the sum of them, then it will give you this x. So now your variable from the x becomes this x1 to and they are binary. And to represent this function in yes is pretty simple. You actually only need the boundary 2 tensor. So it is precisely simple structure. Well, now this T is not a number, but it's two-value index, two-value vector, dimension 2 vector. When it's T, it's also 2 elements. And one of the 2 elements. And if you think about it, it's pretty straightforward that this is prediction. So this certainty that the contribution from index is either 0 if x 1 is 0, or it's 1 over 2. compose your real number. These numbers and each numbers are given by one tensor. If you put it this way, you can automatically sum over all beautifully. I give you an example, like if you just multiply these two tensors, then you get almost the same, but you accumulation, summation of this. So if you multiply all of them, you got keep accumulating this end. But then you get a summation. Then you can, in the end, you can find these two additional tensors to pick up this element. Give you the sum over all the Ti. What is Ti? Ti is just either 0 or its contribution on one of them. So the conclusion is that this is easy to be exactly represented in great power saving formulation too. And you can also do it for the MTO, here. Okay, so here's something there. So, yeah. So if you have the function of x, then it's easy to, subtraction against the square of the function. And this is what I got. I probably won't explain in the code itself, but to show you that this is how what I obtained, which is QPD s, and it's x squared. If you take the derivative, so you can construct the first derivative of the line of x, because it's linear, and then do it again. So, sorry, you got this comes to. Yeah. So, now we have a pretty good control on the function of x squared. And we also have a good representation of this second derivative. Now, combine these two, you begin to how we can solve a simple calculated problem. Right? So now we can make this, this second derivative and x squared together. Then we can put it in the given G, find the ground state. This is what we do here. Running again. And then you can see, so this stage line is the exact function of the ground state, just a thousand. See those main points are we obtained from using the update to be function. This is a finite interpretation because here I just use 5 tensors. If you are not satisfied with 6, then you got double this discretization. Increase the number of discretization points quickly. So, really fine story. So because you go exponentially, you can really easily almost, you can easily go to almost continuous. You have a great state of exponential to very fast position. So for 10 tensors, it is really helpful. Your tensor recognition regards. Yeah. And then I'll show you the last example. And then I can compare this counting state, and I can shift my, body potential theory. And then I can do, then you have a package. I'm staying here, right? But then I can use, take the convolution method in this to do the convolution of and here I'm just showing you the final result. You just take a few seconds to run this. You can see it's funny, it's pretty cute results. You start from Gaussian on one side, and on convolution has been oscillating in the so it's nothing but the standard tensor methods are talking this. Okay, so with this tool, I think I can, I can safely say that more or less every single part of the problem, all the mechanics can be easily solved against this technique. And either identity problem or convolution problem, single wave function, single problem. I think I really like this idea. This is very interesting. This is here that allows you to connect to public applications. So yeah, so I hope you kind of like this idea and maybe you could find some applications. Okay, so let me start my tutorial now. And again, I will put this material in the next. Maybe I can take 2 questions, if there's any. X squared? Yes. Yeah, I did explain this. Yeah, I did explain this. Basically, basically first explain my X. So I have an PS for the X. Right? And basically be the solution of it, maybe it's an MPO. But I require that this is not be diagonal. This is 3 or it's not be 0. 1 plus 1. Then, so this is X. And I apply X to another MPO of X. And this Gaussian. For Gaussian, there's no easy way. So in this application, I solve this Gaussian from solver. But there's a very powerful tool that, let's say, it's a cross application. It's a very powerful tool that can very quickly give you the MPS form of almost arbitrary with a very low one. Right, so that's in practice we use the tool of fit function here structure as a potential. Okay. For example, 1 over R, there's no direction. Or you need to have some smart way of right. Yeah. How do you mind? No, not really. Just
like a period, the different digit.
Yeah, this so it's a bit like that. It's a real space, but each digit is a different scale. The first digit represents the large scale. You put in the first digit 1, left and right, between. And in the last digit, so if you add one additional sign, so your last digit, then you got additional column. When the last digit gives you a small scale, the scale, yeah. All right, so it's the questions and I'll stop here and take the house security order. Oops. Easy part of
So first of all,
the same Darwin for allowing to spend the rest of the system universe supplies here to offer you an example of the potential RG in long-term electron system. Okay. And this topic is very much related to linear resistivity and Chung stretch battle plate that's been discussed in Professor Yu's talk. Yeah, thank you. Yeah, so and this is a very generic and very interesting and serious on many states that is closely related to the algorithm. And so I'll keep my talk short. Okay, so I mentioned already some of the key ideas of this RG steps. The first talk, so I will start by do this. Sorry. Okay, yeah. So I will see this is already starts, so you know very well. There are closely component phase transition or classical phase transition. They're scaling laws and the divergence of correlation events and in a parallel fashion. And to do the RG step, we first do this mode evaluation to integrate over the high energy mode and get the low energy Hamiltonians of this mode. And then we zoom out again the moment and get more range. And then we try to relay the coupling constant before and after this steps. And by doing so, we are able to express the relationship between the different two couplings in terms of the reducing of the momentum cutoff, or in real space, the increase of zoom out here. So this is some detail which I will try in just a moment. And in this ordinary 5-4 theory, we can represent some kind of Ising model and the Ising transition. And Ginsburg now formulate this kind of 5-4 theory where this 5 represents kind of the order parameter. And then we can do RG for this 5-4 theory based on steps that I just mentioned. And I will give you another example which goes beyond the Ginsburg paradigm. So in usual phase transition, we could use the order parameter which is oftentimes the sonic variables. And there's no fermionic freedoms in ordinary standards formula. So, but in modern, say, with strong electron correlations, we have very strange particles that interact among, very exotic particles like spinons, holons, and electrons. Okay. So, and some of these fields are bosons, and some fields are fermions. So you get additional interactions between the fermions or electrons and bosonic freedom. Okay. So therefore, this standard Western Quantum type of formalism of phase transition need to be revised. And I will give you an example in the NTHU phrase that we are able to use this RG steps, get interesting phase of this strength within this kind of perturbed expansion of this competing orders. Okay, so this work was recently posted in the archives, which we proposed a theoretical mechanism to plan this kind of Funkian transparent phase in the NTHU.
first. And these three are my collaborators, Chung and Dr. Kim Raymond. Over time, they are postdocs working. So I will first, just illustrate this strength of this platform. And it is very similar to this heavy Brownian content material. And in heavy Brownian models, we are able to describe this kind of a breakdown condition, which I will require just in a moment. And in Q-frames, there is a very much similar transition that happens in the spin and transverse region, and it happens locally outside. Okay. So it's kind of a local quantum critical point. And we propose the theory to model kind of local quantum-based transition based on this heavy Brownian homology of a complex Hamiltonian. So in the sense, we're thinking about two-dimensional TJ model, and we try to map the TJ model in the strange region to effective Kondo-Heisenberg-like. On each side, we have springing interactions between two very strange fermions, and also there's a Heisenberg anti-ferromagnetic exchange happening between the neighbor gates. So that is what we know from this heavy fermion physics. And now we will argue and find by doing RG that this kind of physics occurs in strength region of Euclid. So based on this kind of a very strange coupling that I just mentioned. So in this strength matter region, there are some very weird strength particles that give rise to the local charge fluctuations. And among them, there are some kind of composite fermions which play the role of electron. And there's some kind of charge neutral spin, fractionalized spin applications coming from spin liquid or Anderson type of RBB spin liquid, which we call spin. And there are also very interesting local charge fluctuations, which are represented by the local boson. So is this three particle interaction that will lead give rise to the linear region groups. And none of this can be easily proved in experiments. In other words, this is very much like a theoretical proposal, but the consequence of this proposal could be compared with experiments in a very good agreement, which I will discuss comparison between this theoretical model where we have kind of three kind of layers of particles, but they live on the same site. It's just three different particles living in neighborhood at the site. One is spinel, and this is and this is say electron, and this is right. Okay, so and this is the paradigm that we is looking for, namely whether this kind of liquid metals could arise from this competition between two ground states and oftentimes near with non-conventional superconductivity mergers. So, but what are these two things? So, this is a very challenging question because in Q-frames there are many competing orders, and we have problem to identify which two phases are the most important, couplings that may play a dominating role, and especially near this continuous transition. So apart from this divergence of spatial correlation lengths, we have in quantum-based transition the divergence of the time correlation. Time component, this time in this field theory, imaginary time represents temperature, because this is what we are familiar with from the Feynman's class integral to represent partition function and find a temperature, then we can define imaginary time, which has interpretation of beta, which is 1 over t. Okay, so near this transition in this pink region, this dynamics, which measures the time correlation function, intertwine with the thermodynamics. That's a very important concept. So we have both content and thermal fluctuations in this region. Okay, so this is the introduction. Typical example we have in front of metals is shown here. Is the experimental data. So in this very weird heavy thermal compounds, they have two phases. One on the left, which is anti-ferromagnetic metal, which shows the square of the liquid temperature sensitivity, and on the right there's a paramagnetic heavy electron mass because heavy liquid, and again shows the square resistivity and low temperature. In the middle, there's a tornado shape of region expanded this field. So the field will point in many astronomical electron systems. So they have both the counters with freedom because they come from this D and S electron. So D electrons are more volatile and F electrons are more localized. Okay, so they have both condo and also the condo mediated KY interaction. So these two phases are very easily straightforwardly identified. This is some kind of anti-ferromagnetic long-range order state with metallic here. And right is condo strings paramagnetic mechanism. Okay, so this phase is condo absent, and this phase shows condo here. So no condo, but long-range order, condo without long-range. It's very easy to identify. So you could really identify this is competition between condo and anti-ferromagnetic object. Okay, so this has been studied for a long time. Okay, so but the simple physics occurs in humorous. So this, I think, many people familiar with this kind of a Hubbard model, which could explain more insulating state of difference and have living. Where you have this again, this anti-ferromagnetic long-range order, and happening is brilliant because very strong concept function. But once we go away from happening, and very interesting phases emerges, and this is a cartoon picture of this phase diagram. As I mentioned, so once you go away from this long-range order phase, you end up having kind of a RBB spin liquid. It's kind of a proposal by Bill Anderson time ago. Inside the pseudo phase, there are many interesting problem symmetry phases like charge density wave, spin density wave, pneumatic, and temperature and so on. But the same features of the so-called pseudo phase, which shows the gap in the spin sector, the charge sector, is that there is some kind of vanishing of this RBB in the Anderson's language, which gives rise to the phase boundary between the pseudo gap and the transmetal in the middle. At the right, if you go over those, the normal state, and this ground state becomes normal metal. So you can see very clearly that it is the hopping of electron in competition with kind of spin interactions, right? So there is some kind of competition between the hopping and Heisenberg exchange, okay? And the inference of the Heisenberg exchange is illustrated in the pseudo-gap, but this kind of RBB physics give rise to the features of space, and in orbital size, it's hopping term is dominance. So we can guess widely that maybe for some strange reason, And near this kind of alleged or putative political point buried inside dome, there is political behaviors due to the competition between pseudo-gases governed by the J and electron hunting governed by T. So the competition between T and J may give rise to very strange behavior. So this is our starting point. And this competition between T and J mimics the heavy Fermi complementary activity, which I will show you just a moment. So not only do we have the linear activity goes to very low temperature, starting from almost room temperatures, 300 Kelvin up to millikelvin temperature without slow change. Okay, so this is the most weird in homology because no phonon can live in the high energy temperature region. But what about the low temperature? So if this is given by electron phonon, and you must expect slow change when you decrease the temperature. But there's no slow change, and it's very generic. And apart from this, there is a divergence, logarithmic divergence of these B coefficients, which come from thermodynamics. CP coefficient, which is given by T over T, shows this beautiful logarithmic divergence. And this two phenomena go side by side. They come together. So in the theory, we need to explain this proof simultaneously. Okay, this is hard. And so this is our starting point, but there is a debate even now whether there really exists a single quantum critical point. Yes, sure.
What's the color representation?
This is the pseudo-gap region. So this is 0.2, 10% of doping. At high temperatures, you get linear, but low temperature, you end up being in the pseudo-gap phase, where you have both spin and charge gap. And that is why you can increase the resistivity. Right? It's most like instantly like, but it's a bad match thing. Okay? But if you strain from the middle and you suppress the conductivity, and you can go generally all the way to the lowest temperature. This is expected data starts here. Okay, it's a fact. Okay. So now we have to consider which scenario, whether there really exists a single point somewhere which connects to crossover scales when you remove superconductivity. But in many experiments, there is some extended region like this whitish empty space here, where you find the stress metal go all the way to 0 temperatures over extended region. So it's not ended at a single point, but extended region, which we call the stress metal phase. Okay, so which was mentioned by Professor Xu. Okay, so is there really a QCP or is it a new phase? We don't know. Experimentally, people are fighting between these two scenarios. They're still fighting now. So the signature of a single critical point comes from two magnitudes. This is a whole coefficient or number across this critical doping, which called star, here is 0.2. And you see the jump, which indicates that the surface volume experiences a jump from a small, large surface. And when you see this jump, this is a reminiscent of this breakdown transition, heavy term. And this is one similarity. And another signature of P is the divergence of gamma coefficient of doping at low temperatures right at this time. You see this shooting up. This is again a signature QCP, again in many conduct materials. So this is in favor of the QCP. However, more recent works in microplastics and operators, so they really find this extended strength metal region when they use our view to suppress the conductivity, you can see here there's no single point, right? But of course, the materials are different. Okay? So would it be possible that depending on materials, you sometimes find this critical behavior, sometimes find general effect. But how come? Okay, is there a unified theory standing to account for both these scenarios? And this is our motivation. See this crossover, smooth crossovers. This is not jump the whole number. So everything is smooth. Okay, what's going on? Okay, and more strikingly, as presented by Professor. So they observe this kind of scenario behavior, which is an indication of functionality, but what kind of critical behavior is that? And in this optical transfer instruments, they extract data to get this scattering rate versus omega over t. They also get this scattering. So this is again indicating of some kind of critical fluctuation. But whether this is associated with QCP or critical phase, and what is the origin of this? Is a problem because this again extends over quite a range in doping. Is everywhere in the middle of the space here. Right? It is doping independent. But we know that if you change doping, you change the popping and you change the jelly, you change everything. But somehow this doesn't change scaling. Scaling is still the same. This is the most exotic phase that we can map. And on the next matter, as I know. So, and there is no explanation except for some proposal back in 1980, proposed by Chen Obama, using so-called marginal from liquid, electrons. Imagine this energy is completely low at this moment, and this could be understood positively, but not again, basically, and we still have a gap between theory and experiment. Okay, so here comes the plot. So I guess which could be extracted from the scattering rate, measurement, and scattering rate is related to sensitivity by its Joule form. Suppose you could extract M star and from other experiments, and you divide the rho by this constant, and you get one of the power. And one of the linear with the universal factor alpha. See it becomes stable by the temperature. So you can see all these materials vary from a two-dimensional, different dome and different compound. They all became almost. So alpha is very close to one. So, and more recently, in this June, there is a more recent discovery, more convincing experiments done on the LSBO by both CT measurements and transport measurements simultaneously over the same doping range. As I mentioned, is there a question? Okay, good. Some echo. Okay, so I have to speak lightly. Okay, so you can see that this follows the pre-factor A, and the M star goes by the one over doping, is doping. So you could plot this doping dependence to this alpha. So alpha depends on A divided by M star times universal. And both A and M star goes by 1 over P. The doping dependence just cancels. So they extract precisely a very much universal alpha, which is almost see that over this range of doping, alpha is 1. So it is actually a more convincing evidence that this place does exist. Okay, so what is going on? And more recently, this same behavior occurs in this metric angle justification. So they go to the normal state, find the linear stability, and they do this analysis one more time, and they can find this pretty much agreement the Chung proposal. So again, this is not our students can understand. Okay, so we come from this DJ model, cover model, trying to make a link between this behavioral physics, encompassing language, and DJ. I use this sort of cerebral approach. And there is a recent McCulloch calculation by a group at Stanford. They calculate Kubo formula, which is proportional to the relation function and the relativity. So they really this up to certain checks. And so this phase does exist in numerical approach model. So this is my question to this numerical people, right? Can someone address this by McCulloch or EMRT? That would be very much appreciated. So, we come from this McCulloch lattice scenario, where these two couplings compete near the conditions. So once the electrons get contact with the moments, then the Fermi surface get enlarged because the electron participates from the surface. That's why you see a jump from a certain volume small to large value. And at the same time, there's some kind of arcane which is the nearest neighbor hyperparamagnetic coupling. It's like a talking combo. So traditionally, in heavy field, we can understand this phase diagram by competition between two different phases. One is long range order, another is heavy from. So there is a point and a temperature you get here, not only here, but this is not the case in Q-phase. We don't have long order. Remember, the anti-magnetic order is already suppressed for doping larger than say 5%. Okay, so we are in pseudo-gap phase. There's no long. What is the competition? This is similarity between Q-phase physics and electronic physics that you do see jump from volume, either jump or the forward in both cases. And the strength metal behavior live precisely in this region. There's indeed a similarity, a striking similarity. So we try to follow this similarity and try to mimic this kind of Kondo breakdown scenario in the TJ model. So for those of you who are familiar with the TJ model, need to explain to you is the kind of decomposition of electron into the spin and the charge polygon. And spinons are fermions and holons are bosons. And holon carry charge but no spin, spinon carry spin no charge. So it's a scenario of spin charge separation. So it's back to this dimensional lambda, but in 2D, we have this kind of scenario, theoretical framework that allows us to partially understand the global phase diagram Q-phase. And there is a constraint which enforces the local occupancy of a slave boson and spin to be 1. And you can solve this model at the mean level where this Heisenberg change will be decomposed in terms of the particle mean field, representing the spinor hopping term, the spinor band. Okay, at the same time, the spinor can actually get this RP Hooker pair, which is represented by delta, and we will see later that by properly mapping this model, we could get the effective heavy formulation for the boson, and the mapping was done in this paper that they tried to define another near space neighbor local fermion like object, which we call this spinor bound state, which you find one spinor and one charge on the neighboring sides. So it's not a real electron operator, but it's almost like an operator. And it represents also the bound electron, right? Okay. So then the starting term become counterlike because you have two front bands. One is called spin, which carry both spin and charge, is effective electron bonds, the whole line, which shows the inverse of the parabola. And another is a spinor band, which come from the spinor hopping of the J-term. So then, the bosons are either condensed or not condensed. So in the case where bosons are not, so there is fluctuations locally due to the heat term that give rise to precisely the 3-layer fluctuations that are introduced in the very beginning. So, but when bosons are condensed, you get a hybridization between effective spinor band and effective electron band. That is precisely the hybridization. Okay, so when this two bands get hybridized, you get normal electron. Because now, when bosons are just some numbers, then it is just a classical C number, and C has the same meaning as there's no difference. In other words, you regain, single electron operator once both get condensed. Okay, so and the J terms still keep the same form as Heisenberg at the NTHU level. So this model shows U1 gauge symmetry, so U1 stable theory historically. But recently there's a twist based on this paper, and this kind of a hollow bound state was proposed by those people to be accepted some years ago to describe the pseudo-gap. So in addition to the being liquid represented by the blue bonds, you have the C, okay, which are green oval with the red arrow. The red represents half spinons, and the green oval represents the nearest neighbor arrow to the spin hollows. So they're mimicking the charge edge. Yes. Sure. Right. That's right. Sure. It will come just next slide. Okay, so this model has been solved at NTHU level by the authors of that paper. There are 4 different regions that we could come up with. One is normal form liquid where bosons are condensed, but there is no delta, there's no B. So this is that phase, okay, representing the heavy frame liquid. And when both all the parameters are bosons condensed, we are in this superconducting state because we need both carry and a charge. Okay, so without charge, these are just neutral carry. But with charge being condensed, we get both charge and spin. Spin combined as a group of pair. So this represents a really big superconducting group of pair. And when delta 0, the B is 0, this is the pseudo-gap phase, where you get spin and charge gap, no from liquid. But most interesting region is kind of U1 recognized from liquid state, where both all the parameters are 0. We get both spin and charge expectations and fluctuations. And this is what we find kind of a critical situation. Okay, so the doping constraint is given by number of C particles because the bosons in this region, the region, are not convex. The number of bosons is 0. Okay, but where do the charges go? The charge must go somewhere, and in order to fix the charge, we need to fix the number of C. C carry charge and spin. Okay, So the constraint is revised in this fashion that we count how many spin pairs of lattice, and therefore we count the number of charge pairs. That's your question. Answer to your question. That's right. This is just at the level, right? So this is just for different NTHU solutions. But we go beyond it. But the advantage of this formulation is that this label contingent model is able to recover this nodal Fermi pockets that has been observed in pseudo-phase of glucose near this antinode, near this nodal region, right? Previously, without adapting this bundle Heisenberg language, this boson theory cannot describe this nodal Fermi pocket. The spin of colons are different quasi-particles. When we do this convolution integral, we look at base coherence. There's no coherent quasi-particle P, but indeed, in experiments, we do see a quasi-particle P, and this Cij helps us to recover this quasi-particle P. So this is from the theory. Okay, so we come from the few solutions, and we do one RG and try to analyze the competition coming from the T term and the J term. Okay, so because in this region, we are left with only fluctuations, so speed fluctuations in terms of RBB and charge fluctuations in terms of the power. Okay, so sets and the run of RG was done by writing down the spectrum actions in a spectrum metal so-called NTHU. Fixed point where we have spin-on band and we have the C band, we can generate C band by taking the perturbation theory, and the phi represents the fluctuation of RBB, which plays a minor role. And these two terms are the leading terms which lead to the competition. The G represents the hopping term in the slave boson or condo formation. And the J term is the this RBB fluctuations. So we can write down the RG equations to study the competition between G and J. Okay, since there are no other parameters left, so these are common fluctuations. Right, so which allows us to do derivation parametrically. We could evaluate this energy of vortex directions based on this construct, compare Green's functions. Right, so this local Green's function, so boson is very crucial to explain this local charge fluctuations. Since these bosons are local objects, this gives rise to all these local self-energies, which means that all the sigmas are momentum independent of T. We do this on the RG. Okay, good. So to come some details. So first, we should analyze the bare scale dimension at Leo's order, which come from by counting the scaling dimensions of different fields. When we do rescaling, remember, we rescale this momentum back to the full range. And at the same time, we need to count the scaling dimension of different electron spin and holon operators. And to do so, we fix the dimensionality to be 2, and the dispersion is described by the linearized dispersion, the spin band, and the Fermi moment is fixed, so that we get this scaling dimension. And from this, we could evaluate the scaling dimension of fields by requiring that the sections of this spin term, the bare level, is scale invariant. Okay, so you count, on both sides, scaling dimension of this stuff, and this must vanish. Okay. So from this condition, you fix the scaling dimension of F. And similarly, you can do the same thing for the C particle, for the phi particle, for the slave boson particle. there's the sets. So when we know the scaling dimension of fields, we can simply just plug in this T and J or G and J term to estimate the scaling dimension of these two couplings, G and J. So we can do the same thing by requiring the scaling variance of this T and J terms. And again, we count the scaling dimension on both sides. Okay, and we know the scaling dimension of F, B, and C. We know the scaling dimension of K and P. K represents the electron momentum, P same boson momentum, and omega and mu. And put it in the equation, left-hand side 0 and the right-hand side has the scaling dimension of G bar and all the other scaling dimension of the fields. Therefore, we know what the scaling dimension of the G under this rescaling. This will appear a linear term equation like this. So the scaling dimension for G is -1/2, where we use this epsilon to represent the difference between dimensionality 2 and the dynamic on Z. Okay, so there's a technique called the epsilon expansion technique, which I'm trying to discuss. But in any case, the first thing we need to estimate is the scaling dimension of these two couplings, which can be found in this equation here. And the next is to evaluate the one loop functions. This is also the tree-level scaling dimension analysis. And this should come to this kind of diagrammatic perturbation theory up to the one loop. So, and remember, when we regain full range of momentum, we need to also rescale wave function. Also, we need to rescale the Hawking constant or vortex direction. And the wave function normalization factor is given by Z5, which is the normalization factor of the wave function. Okay, and the normalization factor for the coupling constant. In this case, they are G and J. Follow the standard definition. Carry the inverse of this Z factor. Then the Z of phi is, roughly speaking, 1 minus this result that calculates from energy. And you integrate over random modes, and you get a lot of sweet divergence of the cell energy and what. And you plug in here to Z5 is 1 minus this diagram. The U is 1 plus factor. Right? And this plus and minus comes from this kind of opposite way, 65 Z 5 and Z U. Right, so specifically, once you get these Z factors, you could formulate the coupling before and after you perform the RG step. And before you perform the RG steps, they're just so-called pair couplings, which are G and J. Once you perform the RG steps, they become G prime, J prime. Right? To get the same form of your Hamiltonian, effective locally Hamiltonian, you need to implement this Z factors like this. Okay, so if you have one F spin-on, so you must multiply the ZF to this minus square root, the power of minus 1/2, which is square root, 1 over square root of ZF. And that is because the one Z pi consists of 2 Z's. So Z5 is the optimization factor of the Green's function, and this Green's function is represented by 2 Fermion boson fields. Right? So if you normalize these fields, you get the F squared, right? Which is more or less equivalent to B5. Right? Okay, good. And similarly for the coupling constant J, you could find that this is given by F inverse because there are 2 spin-ons from spin-ons and inverse B5 one, it's minus 1/2, where there's only one 5, and you get J, which we normalize the test. Right? Yeah, clear?
Straight on. So already for physical coupling for G and J.
So we monitor how the G and J flow on the RG.
Yeah, G is related to
the coupling, and J Heisenberg exchange. So it's the competition between the G and J which gives rise to behavior. That's our proposal. Is that clear? Okay, so this follows standard field theory RG. So if you go to any textbook of RG and then RG, the RG, and you will find this definition. So we follow the standard definition, yes. The pair couplings represent the coupling before you eliminate the mode, hydrogen modes. That's the original Hamiltonian. So you write down Hamiltonian, but you don't do anything. You get a T and J, right? And these T and these J are what we call the pair couplings. So you don't do anything, write down Hamiltonian, and those couplings are called pair couplings. Initial, which means that you come from energy, right? You haven't eliminated this, rings of this state, right? Okay. It's like you don't wear any clothes. Bare. You're naked. Okay, so once you normalize these couplings, you go through the RG steps. Then these couplings were addressed. This is what we call addressed couplings, or normalized couplings. Again, so this is definition of Green's function, right? Right. Okay. So you get psi, which is a fermion or Boltzmann operator, right? Okay. So you could, consider this before you perform the RG, right? Because the field needs to be normalized, right? Okay. So get the original formula. Okay. In order to do so, you need to multiply the field by the renormalization factor Z. Before you multiply the Z, they are just paired. All right, and you see the Green's function in terms of different couplings represent, before and after you perform RG steps. So without prime, they represent the pair Green's functions. With the prime, we call them renormalized Green's function. The pair Green's function is related to normalized Green's function by the factor Z of phi. The Z of phi is related to the self-energy. Clear? That's the RG step. So we simply just need to be very careful when we value these Feynman diagrams, keep track of the plus and minus sign, effect of one half, so on. Right? Okay. So great. So then we follow this definition. We calculate the Z factor. So these are the most tedious calculation that we need to do. Okay? And we need to collect all the leading logarithmic divergence of these diagrams. And then we take the logarithmic derivative of this cutoff, log cutoff, and you get this RG equation. So that is the relation between the prime and unprime. Yes?
Before you analyze language.
Right. Why? This is the step 3. We already eliminated these high energy modes, but we need to rescale the momentum back to this full range. Remember that. But at the same time, we need to normalize the fields and the coupling constants. Otherwise, you don't get back to the original Hamiltonian. This is very important step. You need to rescale everything back. Okay, you multiply the fields and coupling constant by the Z factor. This Z factor are precisely the diagrams that we encounter in high energy physics, right? Those self energy and vortex corrections, and which carry logarithmic divergence. Okay, but here we actually take differentiation of the logarithmic divergence and to relate the G prime and G. And that allows us to get the RG equations. So let me continue. Right, so this is horrible, but durable. Thank you. Right. So, right. So, for example, in this TJ model that we studied, we have 5 self-energy diagrams. Sorry, and they are represented by these two pictures. Namely, we need to remove the high energy modes. Meaning, we need to remove or integrate out the high momentum states and sum over multiple frequencies. So there are 2 summations. One is momentum, another is frequency, which are called multiple frequency. Right. So that is what we right here. P and Pn. P represent momentum, and Pn multiple frequency. So you can relate this internal external momentum and frequency by the momentum conservation and energy or frequency conservation, right? And then you have to sum over the internal equals the free. Okay, so this is what we do. So we don't just sum over the shell, but we sum over the full range. But this is equivalent to perform this partial sum. And at the end of the day, we take the logarithmic derivative of this diagram, in order to take care of this, the corrections due to this mode elimination. Right? So there is a log dependence on this of D. So this is what we are looking for. Okay, so in one loop RT, you get 1 log D factor. For 2 loop RT, you get log D squared. Okay, and so on and so forth. And so we sub at 1 loop order. And that's why we collect all leading log directions coming from these diagrams. Yes?
You know the theory is very reliable.
That's the test. We don't know. But, if we could formulate this RG, and this is renormalizable, okay, we don't know that in the right? So similarly, we could evaluate vortex corrections diagrammatically, at the order of 1 loop. So why is 1 loop? Because this is a loop. This is a loop, and this is the loop. Okay, so 2 loop diagrams is more complicated. Right? And again, we collect all these leading log corrections when we evaluate these diagrams by summing over internal decrease freedom. Is that clear? Right. So once we have done that, we could write down the ZF and ZC and Z5 and ZB and then Z5. Okay. Z5 is the square of this wave function representation factors. Then you plug in the definition of Z5 and ZU inverse, and you collect the leading logarithmic divergence contributions from those diagrams. And then you plug all the Z factors here, and you take the logarithmic derivative of this relations, and then you get this RG equation. Right? Okay. That's clear? That's the procedure. Right? Of course, this is a tedious job that you need to be sure that plus and minus sign factor 1/2 are correct, right? But this is durable, and we can check. Okay, so and we find the non-trivial fixed point somewhere in the perturbative region where both T and J are smaller than 1, which is in the perturbative region, and we move this points to this P and Q to get the RG equations near this R, and I skip some details. So these are the resulting coupled RG equations that come from 1 correction. We can see that we have the CR somewhere in this phase diagram, in a particular region, which separate these four regions. Right? So we already know that these four regions represent 4 fixed points. Okay? And the most interesting point is the CR, where you can imagine that for some materials, when you start to dope the system, you come from this small t, large j limits to the large t, small j region, effectively. Imagine you increase the doping and you get more enhancement of the charge motion, right? Eventually it becomes metal. So this dashed line represents the actual proposed experimental, paths that you increase the doping. Okay, so there are 3 possible paths. The most interesting part is going through the CR. And this is the phase diagram. So you do see a quantum critical point once you remove the superconductivity, but this has not been observed experimentally. Okay, what you have seen are either the path 1, where you have the superconducting dome, or path 3, you completely remove the superconductivity. And the path 3 is what we call the strange metal phase. And path 2, you pass CR, and this is what we propose, the quantum critical. Okay. So, but all the 3 pink regions are related and are controlled by the same CR. That's really what we find. Interesting that suppose you apply the field and suppress the conductivity, and you made just about to suppress the 4 dome, and the 4 dome shrinks to a single point. Suppose we have the situation and you probe all these properties of thermodynamic transport, you may see signature of the quantum critical point. But in case you oversuppress conductivity, and you don't get this point, but instead you cut this phase diagram by a finite segment, indicated by this blue line here. This is precisely what we propose, the strange metal phase. So this is the extended region in over doping, and we further calculate the transport to show that they behave exactly the same. The scattering rate shows Planckian behavior. And therefore, this is what they plan to be the Planckian strange metal phase. And this is what we propose to be QCT buried inside the dome. All right, so to establish the there's a there is what? Right, so this is more localized phase when J becomes relevant and T irrelevant. We go to the most bad metal region, but this is delocalized for obvious reason. Electrons are delocalized. Electrons are more or less localized. So there is a localized, delocalized condition precisely than scenario that we find in the heavy Fromian lattice. Right, so we further calculate T star across the line, which follow this kind of our standard RG definition. So this is linear crossover, and beautifully it covers more linear type of crossover scale T star on both sides. And so here comes the transport. So the transport in local theory come from the self-energy corrections at finite frequency and finite momentum, but since they are local, so they are independent of momentum, so they depend only on the energy or frequency. So so if you calculate the Foucault formula, it reduces to this relaxation rate that you calculate by the self-energy correction. So there is no vortex corrections involving here if self-energy are local. So this is a local critical point, and there's a magic cancellations of the self-energy diagram. Remember this GC shows no dispersion and no dynamics in the beginning, but we generate the band and the omega by the RPA, second order perturbation. So the Green's function of C carry inverse G squared factor. But when we calculate the cell energy, there is another 2 factor of G coming from the diagram. So this G squared cancel, and that's G squared. So you get almost coupling constant independent cell energy. That's more or less what they found. Because G carry the information of the doping. Okay? You change doping, you change G, but the system doesn't know that you change doping because the doping dependence or G dependence, hopping dependence, is cancelled magically at this one loop. And therefore, we get universal scattering rate coming from the cell energy, the zero temperature, finite temperature, scattering conformal temperature in the scattering region, and we find the universal scattering. So this is the direct comparison between our theory and the experiment without fine-tuning parameters. So all these colored curve with the fluctuations are experimental data, and the solid black line comes from our theoretical prediction, and the red dotted line comes from another Poing model like SYK, such as KTF model. We consider the random hopping, random exchange interactions, which I don't know has any relevance for the price, but you can see that both for the slope and the intercept fit extremely well. And this is the universal features of Planck. And the real part of the cell energy gives you this effective mass enhancement. And our theory also has a good agreement, not only the transport, but you calculate local density states coming from this so-called marginal thermoequilibrium cell energy, which was proposed by Saitama and all. And we offer a microscopic mechanism for this marginal thermoequilibrium. And we plug into the single electron Green's function with a proper fitting of the T and T prime. We get almost identical line shape of the output data that was observed by the exchange near the antinodal region of the Q praise in the overdose region. Right, so this is the second agreement. And then we take differentiation of our scattering rate with respect to the omega over T, and we compare this with the hypothesis data, and we cannot distinguish between theory and experiments. So they really fall into the experimental range of data points. So this is a universal. It doesn't depend on doping. It doesn't depend on J. It doesn't depend on G. Right. So over this different temperature and doping range, you get exactly the same schedule, which precisely can be understood in terms of the local critical charge fluctuations. And moreover, we can calculate thermodynamics, the CT position coming from the critical properties of the J. And to cut the story short, we get almost all of divergence of gamma coefficients near this J star fixed point. And this is because we have whole singularities of the spinel band. Spinel band, they'll remember it is at half filling because bosons are not convex, and therefore spinels are exactly half filling. So you get exactly this dimension of the spinel surface, and you can calculate this thermodynamics of the spinel from the surface half filling, and you get precisely this kind of log P corrections with divergent prefactor near this J star. Right, so let me just maybe 1 minute to summarize this scattering mechanism. So we're familiar with the band scattering, right? Umlaut scattering, that's better. But here, for some strange reason, the effective degrees of freedom is split into 2 different scenarios. One is the spinels, another is the electron. And this electron band is very unusual electron band. And these 2 bands could actually get scattered by this forward only scattering. So there is no backward Umlaut scattering. And yet, we could get momentum relaxation because the charge current is split into 2 different ways. One, the charge neutral spin-off current, which doesn't carry charge, there's no current. And another is local fluctuating charge. So somehow electrical current at this interaction split it into different cases, and the charge become local, and the current is carried by the spin-off. So we don't need the backstory mechanism to get this scattering rate, and yet because this effective Kondo Heisenberg-like two-band system, you get mechanism for this getting right. So we could also very straightforwardly explain this crossover between small and large Fermi surface part. Because bosons are condensed, it becomes a larger Fermi surface of normal metal. When bosons are not condensed, so it is a small Fermi surface. So you can very naturally explain the crossover or jump between the small and large Fermi surface. Okay, so let me summarize this kind of simplified, steady boson modified version of the steady boson DJ model by that one of RG help us to quantitatively and quantitatively understand some of the very strange behaviors of cuprate metal. On one hand, there's a quantum critical behavior. On the other hand, it's a strange metal phase, but these two different scenarios are reconciled in a harmonic way within our theoretical framework, meaning we have both scenarios. That's which one is right, which one is wrong. But depending on materials, as function of doping, you may end up having this pass 1 or pass 2 or pass 3. So it depends on material. Okay, if we find the material which is closer to the CR, you may find this. But if you get the material which follows pass 3, you will see this. Okay, so this is a nice calculation that we could definitely access so-called quantum critical point. And we are waiting for future experiments to realize this scenario by introducing doping or disorder or magnetic field. We could may get close enough to see power. Right. So I hope I have convinced you that this is an interesting scenario, and we are waiting for the experiments. And I hope you could get the main idea of the RG procedure in a specific example. So you see, this is different from Landau, because in the Ginsburg Landau, there are no fermion in the tree, right? Phi in the Ginsburg Landau is purely bosonic. But here we get a coupling between the fermion and boson, similar to the electron coupling, but more complicated version of electron fermion boson coupling. Sometimes people call this coupling Yukawa coupling in higher physics, which couples the fermions and the bosons together. So this is one example that we go beyond the Landau paradigm. That we consider this kind of Fermi surface construction across the quantum breakdown transition. Okay, so I apologize for the overtime, but thank you for your attention.
So maybe
so good. But you did mention about what is I understand this doesn't what kind of charging existing.
Right. Yes, I fully agree with you that this kind of local charge fluctuations could be detected by the methods that could detect this CDW trends. Okay, because there's no Q dependence. So you get very broad intensity over the entire Wilhelm zone or entire momentum space, right? So it's a very broad intensity. And this almost Q-independent of a scattering indicates that this is local in origin, right? There is no capital Q vector, which signals long-range charge density wave order, but instead it is a very broad distribution of a charge fluctuation. And we can call this charge density fluctuation as well. But if you go to the very overdose region, and I expect that this distribution would become even broader because you are away from pseudo-gap phase. So over here, people have not really discovered the long-range charge density wave state yet. Okay? But still, you can expect some kind of charge fluctuations all over the place in the in filtrate baseline. So if you measure the charge susceptibility on the overdose sites, slightly overdose sites, you could see an even broader distribution of the intensity, okay, which is one example of this local charge fluctuation.
Yes, sir. What is it? We have
okay. Yes, because they're times 0. There's no true long range of diagonal order. There's no Cooper pair in Q. Only fluctuations. Remember, delta represents Cooper pair. Okay, there's no mean Q amplitude for this pairs, but only fluctuations.
And even at low temperature.
What?
Even at low temperature.
If you remove the superconductivity to the lowest temperature, still this is a stable fixed point. This is what we find by 1 bar G. We don't know that before we calculate. Right? So we start from high temperature fixed point and try to lower the temperature by this RG procedure. So with lower temperature, this state becomes stable. And the reason this is stable is because this RG flow that I mentioned. So it really flowed to the same fixed point. Right? But along the way, the system forget about the fact that the T and J flow to 0 in transport. The transport doesn't know about this shrinking of this hopping term because the hopping term gets cancelled exactly. But this is really weird. So there's 2 couplings flow to 0, but it doesn't reflect in the somewhat in the transport, but it reflects the thermodynamics. Okay. And this is again an indication of a spin charge separation because the transport is responsible mostly by the electron motion, but the thermodynamics they come from both electrons or charge neutral particles, like spinons or magnons that are charge neutral, but the transport is contributed mostly by the charge degrees of freedom. To see these different behaviors in the spin and charge degrees of freedom from theory and also in experiments.
Yeah, maybe.
In your theory,
how can we what?
Because we have very.
That's the long-term goal. So the first thing that we need to understand is how the superconductivity of D wave type emerges from the Planckian metal. This is really a hot topic now, right? So this is highly conventional normal state or matter. And how does this state emerge to the superconductivity? We are studying theoretically. And once we know how this superconductivity emerges from the strand metal, we can optimize the PC by changing T and J or G and J, or I don't know. So proposal for the experimentalists to say change the material properties so that it can actually go higher TC. So you can see that this is the combination of the T and J term, right? You need to optimize the effect of T and J to get a higher TC. So on one hand, you need to increase the J. On the other hand, you need to increase the superfluid density as well. That is this product of these two curves, give you the maximized, window of the speeds, right? This there, this superfluid density. So you need to get a steeper slopes for both delta and rho S, so that the intersection, the product of the curves give you the optimized state. This is the the long-term slope that we try. Another is to apply this theory to study similar behavior in different materials, such as nickel and metric angle variable thing. And so you see the similar Planck behavior emerges, but whether they come from the same origin is a question to be addressed.
Yeah, but you guys already say it.
That's right.
I will choose the
Why do I want?
Let's see.
So we just calculated the one loop order and find
only one. Yes.
Right, but they all come to play because there's a relation between G prime and G, right? So F actually connects two coupling couplings.
Anyone down with it?
So the best I can say is all divergent diagrams contribute to the RG. Right. So you see there are no corrections here and this one. Okay, but there's some. But we need to analyze which one dominates. But I think they are at the same order of magnitude. Okay. I was running late, so
let me take some. Okay. You also often find these spiral state, so spatial combination of characteristics. See, including this.
No, no, we are not considering the CW stripes because we just use a very simple picture that the Anderson's RBB is in competition with the hopping, right? But inside the pseudogate effect, there are many small regions with different orders, and that could be addressed later by, studying this kind of pseudogate effect. Right? Imagine we include the fluctuations to the pseudogate effect, and by considering, for example, the pi plot space. This has been proposed to give rise to CDW, the pi plot space, but we are not using this pi plots. Okay, but in principle, the theory may be able to, get the CDW and time reversal breaking in the pseudogap region. This is again a future direction. This is a Manila version of the Planck method.
So, yeah, let's take a speaker. Close program today, and we'll see you tomorrow.